Dear colleagues, welcome to the 9th edition of HighMatTech International Materials Science Conference. Before we begin with our official part, I would like to give you a small reminder about the organizational matters that are pertaining to our conference. So we have 7 symposia this year, each one approximately a day, some of them less than a day and some more. On Wednesday, because we have a 5-day conference, on Wednesday we have 2 parallel symposiums, which will be organized here and also in another place here at the Institute for Problems of Material Sciences. And also each symposia is organized by different organizations participating in the conference efforts. And thus it will be also the offline venue will also be available in the respective cities, Lviv, Dnipro, Kharkiv, and of course Kyiv. The structure is more or less the same. So we start with the keynote presentations, then followed by oral session. And typically by the end of the day, we have a session for so-called flash presentations, which are a replacement for poster presentations. And these are 5 minutes brief presentation with presentations with a single slide. So a little bit on technical details. If you participating offline, so in one of our offline venues, please come to your symposium a little bit before it starts. And if you have an oral presentation, upload it with the technical team, so they can start the presentation. If you are taking part online, please be ready to open your presentation properly. So best way to do that is to share the whole screen when you are presenting, and then open presentation full screen. Small reminder about the timing. Please adhere to the timing because the schedule is tight. Keynote presentations span 30 minutes for the talk and 10 minutes for the discussion. Oral presentations, 15 minutes plus 5 minutes for discussion. And again, to put some emphasis on the poster sessions, these are very special. We gathered all your single slide presentations already, most of, if not all, most of them. Those of you who didn't submit the slide, please submit. Please do it as soon as possible. And the presenters should be ready, should sit in the nearest place to the presentation stand, so that we can exchange the presenters quickly. And we will switch your posters automatically during that session. We will also have several coffee breaks, and in the middle of each day we will take a longer break for lunch, which you can spend as you typically do. On that, I hope everything is more or less clear. The organizing committee wishes you productive meetings and successful presentation of your results, and all the best during this time with the conference. And now I submit the floor to the scientific secretary of the conference, Dr. Marina Storozhen, please.
Good morning, dear ladies and gentlemen. It's great pleasure for me, on behalf of the organizing committee, to extend a warm welcome to all participants of the 9th edition of International Material Science Conference, HighMatTech. Thank you all for dedicating your time to join us today. This edition of the conference is truly unique. Why? Because in terms of participant numbers, it's the largest conference ever organized by Francevich Ukrainian Materials Research Society. Today, many Ukrainian scientists are gathering in person across 4 major cities: Lviv, Kyiv, Dnipro, Kharkiv. We meet to discuss the important issues in material science. Moreover, we are honored that many international participants are joining us today online from Germany, France, Spain, Portugal, Italy, Poland, the Czech Republic, Slovakia, Romania, Slovenia, the USA, Mexico, Chile, China, Turkey, and Australia. So in total, this year, we have participants from every continent except Antarctica, but who knows? To all our international friends, both those who have been with us for a long time and those joining us this year, I would like to say thank you. Your participation is not just conference participation, it's great support of Materials Research Society in Ukraine. Thank you. Organizing this conference, every conference is a great challenge, always, but especially under wartime. And it would have been impossible without the dedication of our scientific committee. I extend my deepest thanks for their work in both promoting the event and reviewing all submissions. However, while every member's effort is deeply appreciated, I would like to give special recognitions to the following reviewers for their exceptional dedication to the peer review process: Ганна Кононенко, Олена Окхей, Олексій Міленін, Ганна Бородянська, Наталія Вігільнянська, Ольга Звірко, Роман Явецький, Юрій Плевачук, Олена Сич, Олександр Смоляков, Валерій Скришевський, Юрій Богомол, Наталія Тоговицька, Максим Антонов, Олександр Васильєв, Олег Васильків, Олена Лавриненко, and Галина Крачковська. Thank you very much for helping us. And of course, we extend our deepest thanks to the armed forces of Ukraine for making this day possible. We recognize the terrible price of the opportunity to live and work in independent Ukraine. Every day, the Russian invasion claims lives, and we must never forget the sacrifice of all who laid down their lives for freedom and democracy. And now I am asking you to honor the memory of all fallen defenders, volunteers, and civilians with a minute of silence. Glory to the armed forces of Ukraine. Thank you all. And now we are starting our conference according to the program. And it's a great pleasure for me to invite the president of Francevich Ukrainian Materials Research Society, Professor Andriy Ragula, with greetings. Please.
Good morning, ladies and gentlemen. Good morning to country. Good morning to foreign guests. Sorry. Yeah, I'm sorry for this timing. So, dear colleagues, dear foreign guests, шановні українці, I beg pardon of foreign representatives of this conference. I would like to speak several words in Ukrainian and welcome Ukrainian Research Society. Шановні українці, це дуже добре, що сьогодні ми вже 9-й раз святкуємо конференцію HighMatTech. Це дуже добре, що ми зібралися в кількості більш ніж 200 учасників для того, щоб поговорити про науку, про життя, обмінятися інформацією, згадати про наших знайомих, про наших рідних, а також поспілкуватися з представниками закордонної науки. Іноді це наші колишні громадяни, і тому дуже приємно, що нас підтримує українська спільнота не тільки в країні, але ж і за її кордонами. Ви знаєте, що це дуже важкі часи зараз ми з вами переживаємо, і тому наш внесок в нашу спільну перемогу в цій війні – це в тому числі зібрання разом і робота разом над тими проблемами, які ми звикли працювати. Я хочу сьогодні надіслати вам надзвичайну доповідь, яка торкається не тільки наших з вами справ, але ж більш широкої агенди. Dear friends, dear colleagues from the foreign countries, it is my great pleasure to welcome all of you for the 9th HighMatTech conference. We're happy to have a hybrid format this year and invoke many scientific community from largest cities in Ukraine. You will see many representatives of very famous institutions, sometimes companies, and many representatives of universities. So we're happy to unite people from these cities, from this scientific community, and welcome other cities of Ukraine. And we're happy to welcome other representatives of Ukrainian community abroad. So as a president of Material Research Society of Ukraine, I would like to thank organizing committee very much because they spent a lot of troubles since October of the last year and spent around a year to organize this forum for you, to allow you communications, fruitful communications about modern problems of science, of materials. Let me announce the 9th HighMatTech conference open. Thank you.
Thank you, Professor Andriy Ragula. And it's my pleasure to invite again Professor Andriy Ragula for his plenary speech, Advanced Long-Lasting Materials for Infrastructure, from idea to smart specialization of Ukraine in the European Union.
Thank you very much. Ladies and gentlemen, 10 years ago, President Patton, President of National Academy of Science of Ukraine, was asking Academy. Now we signed agreement with Horizon 2020, signed agreement about collaboration with European Union in the field of Horizon 2020, largest program of European Union at the time. And my question is, what can we do? What can we prepare something very special and propose very special to European community and world community on behalf of science community in Ukraine? The answer was a formulated idea for European technology program within Horizon 2020 to develop the market segment for long life materials in industrial, transport, and energy infrastructure. We thoroughly studied the state of the infrastructure in Europe and Ukraine and concluded that we were facing a large-scale problem. The next slide, please. Can I rule it? Okay. At that time, no one in Europe was systematically working on upgrading infrastructure and advanced materials, and no corresponding scientific and technical program had been created. In the past 10 years, significant attention has been paid to the development of long-life materials in infrastructure worldwide. This segment of market is being created slowly and gradually and through the efforts of people from different countries. For Ukraine, the challenges of operating modern industrial, transport, and energy infrastructure have become significantly more acute due to the war and massive destruction of infrastructure. The challenge of creating new infrastructure everywhere rises, since repaired infrastructure will not allow the country, Ukraine, to quickly recover and develop in post-war period. A niche for Ukrainian material scientists is still open in creating specialist materials for long-life infrastructure. Depending on the efforts of scientists, the volume of intellectual property, the number of quality of technologies, and the availability of variable materials, Ukraine can develop a long-lasting material segment and become an exporter. It's important to focus intellectual resources on this. The "we buy everything" policy hasn't paid off. Developments and specialists are falling into disuse in this case. Let's consider challenges worldwide. Okay, this one. I would name population is growing, mineral resources are limited, European safe life concept is in the deep contradiction against real aging infrastructure across Europe, including Ukraine. The existential challenge for Ukraine is war for now. Population is approaching 9 billion people, and increase in demand and the consumption of material resources is likely to double over the next 40 years. Human impact on the environment in terms of production, consumption, irreversibility, worsen in case of further exploitation of obsolete production technology, industry, services, and infrastructure. Mineral resources are limited, thus, mankind is looking for materials that meet the scientific and technical requirements of continuous operation for a long duration, determined by reducing the technical and economic parameters to a critical level and pollution below acceptable standards, and so on. From David Bauer, we do not inherit in land from our fathers, we take it along from our children. European safe life concept is in deep contradiction with real aging infrastructure across Europe, including Ukraine. In the frame of old paradigm, it has been stated in the project Safe Life Act, extension management of age infrastructure networks and industrial plants. They found the safe use and the subsequent development of European transport, industrial, and energy infrastructure faces considerable difficulties due to their age. The first conclusion concerns one of the biggest problems on safety is the degradation of materials and constructions. A good knowledge of the degradation mechanism is crucial to be able to warn and evaluate properly the resilience of the systems. Nevertheless, there is no European R&D program focused exactly on this problem. To our best knowledge, it must be overcome using modern materials, especially oriented on the long-term operation. Annual damages of the infrastructure in Europe are prognosed. The losses are at the level of 3.4 billion annually, and until 2080s should be increased up to 37 billion a year in today's prices. French Transport Ministry had been warned that 840 bridges, about 1/3 of those maintained by the state, could be at the risk of collapse if not reinforced. Germany's Federal Highway Research Institute found that while only 12.4% of the country's road bridges are in the bad conditions. And Andre Federici from Switzerland stated that we had been having discussion about this for 40 years or more now. So the problem is stay lagging behind the real consideration of the governments, European Union government, and of course the government in Ukraine. Direct damage of Ukraine's infrastructure from the war reached more than 200 billion in 2025. Since the beginning of Russia's full-scale invasion, the total amount of direct damage to Ukrainians' infrastructure has reached almost 170 billion. The figure is given on November of 2024. Residential buildings suffered the most, with losses estimated at 60 billion. 236,000 objects were damaged or destroyed, including 209,000 private houses, 27,000 high-rise buildings, and another 600 dormitories. The greatest destruction was recorded in Donetsk, Kharkiv, Lugansk, Kiev, Chernihiv, and Kherson regions. The damage of the transportation infrastructure amounted 38.5 billion. More than 26,000 kilometers of roads have been destroyed. Losses in the railroad sector amount 4.3 billion. Port infrastructure about 1 billion, and the aviation more than 2 billion. The energy sector suffered losses of 14.6 billion. Industry, construction, and services lost almost 15 billion, and the agriculture sector more than $10 billion. We have an urgent message from Infrastructure of United States of America, the founder of managing director of the company, dealing with this topic, pronounced that America's bridges, roads, and dams are in bad shape. The American Society of Civil Engineers estimates that US needs 3.6 trillion in infrastructure investment by the end of the decade, and the highest score they have on their most recent infrastructure report card was a B+. 10 of the 16 categories received the grade of D or D-. So bad investment sign. So from these points, we may conclude that the problem of modern infrastructure exists around the globe. This is not Ukrainian problem. This is not a problem of some European countries, and this is a problem existing around the globe. The question from nearest and peaceful future should come to us. Does Ukraine plan to develop the transport, energy, industry, infrastructure of tomorrow using own technologies and intellectual property rights? Does Ukraine need substantially operating transport corridors connecting EU with the 4 billion Asia? Does Ukraine really wish to have safely operating energy conversion and supply system? Does Ukraine want to develop fully automated industry facilities operating with a minimal human impact and mostly driving by artificial intelligence? If yes, which materials all these things will be made from? Certainly not from those kept in the granddaddy's backroom. To my mind, Ukraine must generate as many as possible new diversified materials and technologies of their production to rebuild, modernize infrastructure in the country after the war. The material research community, UMRS, must create a new specialist class of resource materials for infrastructure to increase the quality and reliability of transport services, energy efficiency, high environment friendliness, and thus reduce overhead cost and or increase the competitiveness of Ukrainian products at regional and global levels. There is no country in the world focusing its economics exactly on production of materials for infrastructure. There is a very good chance for us, for Ukrainians, to start producing something very special, unique, and necessary worldwide to be sold. Let me give a definition what we are talking about when we introduce the term resource materials. One of the most integral characteristics of these materials has been and remains the resource of the service under given conditions of exploitation. We define the resource materials as available smart materials of new generation which meet the scientifically and technically sound requirements of pre-assigned resource objects for long-lasting continuous operation. The synonyms are long-lasting, sustainable, resilient materials, very often used now in scientific and engineering papers and reviews. Resource materials for 100-year service is in transport infrastructure, energy, industry, environment protection infrastructure. Long-lasting materials are very welcome in medicine. Structural materials are mostly steels, polar metals, concrete, fibers, polymers, and composites. Exactly those we deal with, but not focus on. Functional low degradable materials for infrastructure are very diverse. Let me give you some examples, because without any examples, difficult to accept statements I give you. The first example from US, the carbon fiber reinforced polymer bridges. You can see the pedestrian bridge over here and the automotive bridge on the left slide. Then basalt fibers reinforced polymer bridge. These are working solutions, operating solutions already. Basalt fibers for asphalt pavements and overlays. And you can see the comparison in price between basalt threads and steel rebar. So this rebar is made from basalt with polymers, and here the steel. Independently on the type, 8 millimeters to 22 millimeters of rebar, we have a very competitive price as compared to conventional steel rebars. Groundbreaking ideas for resource materials. Sustainable materials for infrastructure include natural resources like bamboo, reclaimed wood, and cork, recycled materials such as recycled steel and recycled glass, and innovative options like hempcrete, mycelium, and low-carbon concrete. These materials reduce environmental impact by being renewable, biodegradable, or delivered from landfills, promoting a greener, a more resilient future of the construction industry. I'd like to give you several examples: carbon-based reinforced concretes, self-healing concrete, hemp rebar, ultra-strong plastics, ultra-thin solar cells. The carbon fiber reinforced concrete. The Cube is pioneering an architectural project by Han Architekten and the Technical University of Dresden. They proposed quite interesting solution of complex shaped building made from the concrete reinforced with carbon fiber. Carbon fiber can be used to reinforce concretes, not only for building. So you see the competitive figures. So this is density for carbon fibers. This is strength in gigapascals. This is elastic modulus. All figures are quite competitive with respect to steel reinforcement of any concretes widely used now in the world. And you can compare, we have much lighter construction in the case of carbon fiber reinforcement of concrete, and approximately 7 times much higher tensile strength as compared to steel. And elastic model is also quite high in the case of carbon fiber. In this case, we have a chance to develop much more stably operating infrastructure from the concretes. Self-healing materials. So this is very rich agenda to work together, chemists and material scientists. Self-healing steel is a revolutionary material designed to repair its own damage, extending its lifespan and enhancing structural integrity. Through the incorporation of the specific healing mechanisms, this type of steel can autonomously detect and heal microcracks or damage caused by external factors such as corrosion, fatigue, or impact. How many minutes? Okay. Okay, probably I have to skip, don't read it. Self-healing steels. So there are book publications already. This is not distinct papers, just we have books prepared and dedicated mostly to self-healing steels. And the knowledge confirmed that it could be inserted some inclusions to the body of steels to protect them against corrosion, against further spread of cracks inside the steel body, and so on. So the very helpful mechanism of healing is provided. The same works for polymeric materials and polymer matrix composites. You can see some inclusions which contain some healing components in the case of cracking across these inclusions. So the healing components appear and heal the crack, first of all, as a liquid and a polymerous component, and then as a solid component, completely removing the crack activity from the solid body. The same mechanism is provided for many materials, including ceramics, including metallic materials, and so on. The self-healing ability is the most crucial property of natural systems for survival in unexpected situations in variable environments. The intriguing self-healing polymers and fascinating mechanisms of self-healable energy harvesting devices, such as turboelectric magnetogenerators and storage devices like supercapacitors and batteries, from the aspect of electrodes and electrolytes, represent bright examples of the rapid developing area. self-healing concrete is a very much attractive solid body because our roads and constructions consist of the concrete. But the example had been found in Rome. So if you look at this 2,000 years old dome on some of cathedral in the Rome, you will find that there is a self-healing mechanism inside. This is an explanation of 2,000 years service, because they propose to introduce other type of quicklime to the body of concrete, and after cracking, so the water go to the quicklime, so invoking the chemical reaction inside and healing the crack. So this is a good example, which is the basis for the development of new solutions. Hemp rebar is the potential or triple the service life of buildings, bridges, and other infrastructures, especially in high salt environment. You know, there is a problem for iron rebar to be crusted a lot, especially in the salt environments, in seawater. In this case, this sort of concrete is not stable, but the hemp rebar demonstrates high stability, and the market is growing pretty fast with this sort of material. Ultra strong plastics. The chemical engineering engineers in Massachusetts Institute of Technology invented super strong plastic, which is both light and moldable, yet both and the strength twice that of steel. So we have quite seriously reinforced materials for construction application, and the new lightweight materials stronger than steel can be produced from the polymeric materials. You see these figures, 2D elastic modulus and yield strength of 15 GPa for novel plastic, and the bend strength is at the level of 500 megapascals respectively. Energy infrastructure also requires new material solutions. So there are energy harvesting conversions, energy storage materials, energy transmission and distribution, and smart grid and distributed systems. People invented the ultra thin solar cells with a term of exploitation longer than conventional silicon single crystal based. So there is a statement that the weighting 100 of conventional solar cell panels yet. So it's much lighter and generated 18 times more power than per kilogram as compared to conventional solar cells. So you can see several examples operating as the coatings, the freestanding films, some elements of flying machines, and stationary solar electric power stations. So what's going on in Ukraine? In spite of war, the ministries of energy and transport proposed a vision of transport infrastructure development in the country, after war, and also rebuild of the energy supply systems based on novel developments in materials as well. So, and you can refer to these books and look through these books. They keep information about potential materials interesting for application in both infrastructures. I wanted to get talks about the role of artificial intelligence in the infrastructure. The collection and processing of colossal amounts of data from continuous infrastructure monitoring necessitates the use of artificial intelligence in infrastructure safety and management tasks. Imagine if you paste a lot of gauges or sensors along the infrastructure of transport, along the reactors in energy infrastructure. So you may collect plenty of data, and the treatment of this data may be fruitful only using artificial intelligence. For instance, people are looking at this problem quite precisely at this moment. You see the recent review dedicated to application of artificial intelligence in energy materials, and you see the abrupt growth of the number of publications in this field. The same concerning the energy engineering, it's necessary to state that artificial intelligence analyzes complex data to improve energy distribution, forecast demand, and accelerates the discovery of new materials for clean energy technology. Some recent publications worldwide, these are examples of very big reviews on this matter. And if we look at the Nature Communication recently published the paper about electricity-driven mobility, circular economy with the life-scale carbon footprints for climate adaptive carbon neutrality transformation, also very useful publication for understanding the main trend in materials development for these applications. Artificial intelligence, of course, speeds up the transportation engineering. So also grounding on a huge number of data, how the infrastructure is exploited. So we're able to improve substantially not only movement, but the exploitation, this infrastructure as material solution mostly, and have hints from the artificial intelligence which materials should be applied for the next steps of infrastructure development. I'd like to elucidate a little bit funding opportunities, because no one initiative can exist without funding. Really, we have various sources. At least we can start from the internal sources, national program resources materials, funding from National Academy of Science, but the step by step, the calls appear in Horizon Europe program and probably in FP7 since 2028. We also rely upon investments from the private investors and private public partnership with domestic and international businesses at the level of TRL 6. To illustrate my words, I would like to announce that we have already announced 5 calls about photovoltaics, more sustainable, extending the lifetime. You see, people in Europe are thinking, and companies mostly thinking about extension of lifetime, the conventional silicon based solar cells. We're talking about application of artificial intelligence and big data as for infrastructure materials. Then I would focus here innovating construction materials here also exist. And as for ionic batteries applications and widening of production, so also there are necessities in production of new, much more reliable solutions in these devices. So I would tell you that these are not 5 calls. In fact, each of them includes many calls inside. So, and from the Horizon Europe, the Euro Commission decided to fund more than 300 million euro for these calls. So this is a place for our competition as well. And in conclusion, I wanted to tell you that the long-lasting materials could be the subject of smart specialization of Ukraine in the global economy. When we signed association with the European Union, so it was a question, what should be the smart specialization of Ukraine in European economy? So the answer was first agriculture, but we industrial country. We are a well-developed industrial country, at least before the war. And we have a great potential of scientists, engineers, and plant owners, so working effectively exactly in the high technologies and deep technology side. So therefore, it would be true, it would be fine if Ukrainian scientists, together with power people, found the appropriate solution how to enter and contribute to this segment of market of long-lasting materials. Look at these figures predicted by the Institute of Economy. Lord Stern issued this document 10 years ago, predicted that 90 trillion will be invested into infrastructure worldwide for 15 years. So, and this is true. The funding is growing year by year, and we have to contribute here. If we are strong in material science, we have to contribute to materials working in long-lasting infrastructure. This is a task. For these purposes, I would say that we have prerequisite at least big material science community in 16 institutes of Academy of Science of Ukraine, including Materials Institute, including Physics Institute, semiconductors, then chemical institutions, and so on. All of them work in the area of materials. And we have quite good collection of university and very powerful potential over there, also focused on materials. And we have well-developed industrial potential of Ukraine, some of them unfortunately damaged, but totally we have almost 6 million jobs in this enterprise dealing with material production. Yeah, thank you very much for listening. I look forward optimistically to the future of Ukraine and material science community in Ukraine if developing so-called resource materials. Thank you.
Thank you, Professor Andrei Rakula, for a very interesting and I think very useful plenary speech. And now we have some time for the discussion. So colleagues, please, who have questions, please raise your hands.
Maybe later on.
Thank you very much for a really insightful speech and presentation. I hope we will really be able as a country to focus around this perspective direction. I have a few probably more tactical questions, less strategic, let's say. You mentioned artificial intelligence. Maybe let's, may I have two questions here?
Yes, yes.
I will put them in relation with one another. What you mentioned shows that people are already doing a lot, I mean, outside of Ukraine, around the world, around the globe. The situation is again like that. We have to catch up. The question is, do you think we can, without some special idea around that? Am I getting clearly?
Yeah, I agree. This question, in fact, exists. So I'm not sure about some new ideas around AI application. Because it's already works. Moreover, we are not pioneers in development of artificial intelligence. So there are algorithms specifically oriented to the infrastructure ruling, but I would say if we apply this specifically to the development of materials, so it would be some sort of pioneer solution. In spite of existing opinions from the scientific community worldwide, that it should be helpful. It should be very, it should be very competitive. In fact, those who already worked in this area are already in champion position with respect to us. As far as I mean, Ukrainian Material Research Society, we are in Academy of Science as a leader of science in the country. We are scientists in universities are not still defined if we need to apply AI in research activities. There is a big discussion about this, and there is two camps in this area. The largest one belong to elder generation of people. They deny totally application of AI. So and they think that the knowledge of skilled scientists much fruitful as compared advising of AI. But the other part is younger, of course. They wanted to proceed pretty quickly to the competitive environment because advising from somewhere. So they consider fruitful for their career and for their success, of course. And therefore, the competition between two camps will be lost in our country. for next years, but to my mind, we have to apply much forces to try to apply the AI in our research activities.
Thank you.
Thank you. Who else?
May
No
I ask
questions?
a question?
Yes.
Thank you, Professor Regula, for your very interesting speech. I have one particular, very small question. You mentioned mycelium as a component of composite materials.
Yep.
Usually, engineers try to avoid mushroom, fungi in the constructions. Can you give us examples of where mycelium is beneficial? Thank you.
Interesting question. I would answer you with the aid of my personal vision of material science paradigm to use weak chemical bonding. So to develop unique structures, so which can be transformed further to the strong chemical bonds using other operations, but the initial must happen exactly at the beginning using the soft bonding. So in this case, this substance, one of the appropriate substance in the world existing globally, which can be fruitfully used to develop the soft bonded structures. So this is my answer.
Thank you. Are there any questions? No?
Maybe online.
Maybe online? No? So if we have some minutes, so I have questions. I think it's a really optimistic vision, and I think we have many developments in the field of material science here in Ukraine. But what's about the realization? What should be the main steps to realize this concept into the practical vision?
Okay, I already showed this in my presentation. The step-by-step means first to take part in European and national projects which are dedicated exactly to the materials with long-term resource of exploitation. So just to have the portfolio of IPR. If we have this portfolio, there is a subject to agitate people from industry, from business to work with this IPR and transform them into real production. First of all, on the small scale, so this is not prohibited for scientists to create small companies. If you have something unique, and this field of research is definitely unique, and you can offer something like in Dresden University, they simply added the carbon fibers into concrete and demonstrated the small pavilion in the city. It works. So, and therefore, this is the best evidence for a community which has money to invest more and develop new buildings, architectures, and many industrial buildings using these new technologies. So I would conclude that there is the chain of actions, but from the materials community, I mostly expect to see novel groundbreaking solutions, unusual solutions. This is a manner to demonstrate that we have something very special to world community, including community of small investor, medium investors, and so on, and start working with them.
So key point is the stronger communication in cooperation. Yes, not only because industry and science, but inside the science, the research institution. Yes. Okay.
I would add, now the topics of our research is pretty broad for such country like Ukraine.
But I think government also should be involved in such communication and cooperation.
Yes. Yes, first of all, we have to introduce this vision to the government people, like it has been done before during the Poroshenko time. So now we have renewed this communication with new people in government. Of course, we have to save these feelings of future to their brains. So they have to know that there is such an opportunity and there is a chance to work over this opportunity, because we don't have other opportunities to develop other segments of market in the world, because they are busy, because people are working there much stronger than we do that. So therefore, it would be nice to start from something unique and proceed to deliver unique knowledge to the other community of science worldwide, and engineering, of course.
Okay, thank you very much. And we should go forward. So thank you. Okay. It's just, I would like to just remind to all participants that the video recording of the conference will be available on the HighMatTech website, and all participants can watch again the presentation of our speakers, including our plenary speakers also. Dear participants, as I mentioned it before, the organization of the conference is a challenge, and it requires the joining of efforts of many people. And now I would like to say thank you to our sponsors for their financial support of our event. And today we have some sponsors. It's LEM Ukraine, Stasenko and Partners, New Tech, Ukrlbazalt Tizol, and Nech Company. And now I am inviting to the representative of our general sponsor, LEM Ukraine. It's Oksana Rudik, with his speech about methods of analysis of advanced materials. Please, Oksana. Чекать? Немає. Давайте я вам дам мікрофон краще, так? One minute.
Good morning, everyone. While we are waiting, I want to say thank you very much to the organizers for the invitation and opportunity to represent our systems. Today, my presentation will be not about materials, it will be more about systems for materials, for research different materials. While waiting, during all week, we have a small booth in the hall, so you can come to us, ask any questions. And also we have 2 demo instruments from our partners. We have a Raman spectrometer, mini Raman spectrometer, and a regime Raman spectrometer from company like Nova. So please come to us and you can try the instruments in the work.
Okay.
Yeah.
Not okay. Yeah, okay. Okay, we can start.
So, as I told, I will be to tell about methods of analysis of advanced materials. And let me introduce myself, yes, and our company. I am Oksana Rudik. I am director of LEM Ukraine, and our team works together in the field of supply and analytical equipment more than 15 years in Ukraine. We suggest not only instrument in box, we suggest full decision. It includes instruments, installation, training, methodic support, and warranty and post-warranty support. Our office and our service center are located in Kyiv. Now we are official distributor of 4 companies. It's TA Instruments. TA Instruments is a world leader in manufacturing of systems for thermal analysis, microcalorimetry, rheology, and mechanical analysis. Now it's a part of Waters Corporation, but it was started as a division of DuPont Company. And, Micromeritics, now it's a part of Malvern Analytical Corporation, and Micromeritics provides world-leading technology of characterization of particles, powders, and porous materials. NIRLab is a young company in Switzerland, and this company suggests decision in the field of near-infrared spectroscopy. And also LightNova. LightNova is a company with Ukrainian soul, because the biggest part of company and CEO of company is our guy from Ukraine. And this company was created like as a spin-off from the Technical University of Denmark. And the main idea was create affordable system, Raman spectrometers and Raman microscopes, and with high performance qualities. That's a little bit more about each company. TA Instruments. So TA Instruments measured is mass and size of samples under temperature and force. So, and TA Instruments suggests instruments for thermal analysis, microcalorimetry, rheology, thermophysical properties, and mechanical analysis. In the category of thermal analyzers, we can find differential scanning calorimeters, stereogrammetric analyzers, simultaneous thermal analyzers, as we know in our territories, derivatograph. High pressure thermogravimetric analyzers, sorption analyzers, and also thermomechanical analyzers. These systems help us to determine such parameters as glass transition, melting, thermal stability and oxidative stability, sorption, kinetics, coefficient of the thermal expansion, and other parameters. Microcalorimetry. We have a rapid screening differential scanning calorimeter, nano-differential scanning calorimeters, is a thermal titration calorimeters. These 3 types of systems we can use for analysis of biomolecules and for determination of stability of biomolecules, and also for detection of binding processes. And also we have isothermal microcalorimeters. With this system we can use not only for the biomolecules, also it can be used for composites, for high energetic materials. For example, one of the main application is analysis high energetic materials, explosives according NATO standards, STANEX. And also we can use for the analysis of hydration processes of cement and concrete. Rheology. It's, for my opinion, it's very interesting, but not easy science, yes. But now it became more popular and popular in different countries, and I hope it will be popular in Ukraine. This method help us to detect viscosity and viscoelasticity, and can be applied to different samples. For example, it can be paints, polymers, composites, pharmaceutical samples, glasses. And in this category also we have high temperature viscosimeter. It the main solution, the main application is glasses, analysis of glasses. Okay. And thanks to a big number of accessories, we can use more properties of materials. Also, TA suggests dilatometers. TA suggests all type of dilatometers. It's a typical horizontal dilatometers. Vertical dilatometers, it's for sintering processes. Also, it can be it's optical dilatometers. Optical dilatometers can be used for films and very sensitive samples. Quenching dilatometers, it can be used for alloys, steel, and they can you can analyze samples by quenching dilatometers under conditions that the same as in real life. And also we have heating microscope. The main solution, it's a best solution, I think, for the detection sintering processes in ceramics. And thermal conductivity and diffusivity. GA suggests instruments in a wide range of temperatures and wide range of thermal conductivity. So you can easily find the best solution for your sample. And mechanical analysis. Here we have a dynamic mechanical analyzer and also electroforce family of instruments. These instruments can help to detect storage modulus, loss modulus, and electroforce mechanical test system can help analyze stability of materials and their life cycle. The common mechanical test techniques is fatigue, dynamical mechanical analysis, bending, torsion, shear, creep, pulsative, and others. Next company, Micromeritics. Micromeritics suggests instruments for characterization of particles, powders, and porous materials. And here we can find instruments for hemabsorption, gas absorption, density. Can also Micromeritics suggests powder flow analyzers, it's powder rheometer, particle size analyzers, and reactors. Reactors help us to control a chemical reaction like in real life. And a few words about the most popular systems. It's AccuPeak. It helps us to detect density, true density. It's a rapid and precise phase area analyzer, Gemini. And this system can work in different methods. And it's a particle size analyzer, SediGraph. It helps us to detect inorganic particle size distribution by X-ray sedimentation. And one of the main application of in the micromeritic instruments is in the field of net zero technologies. Micromeritics suggests not only one instrument, it's a number of instruments for research in the field of hydrogen production and storage, in the field of CO2 storage and capture. And here we can find number of systems, yes, and this analysis for analysis of absorbents and membranes, and also systems for the analysis of catalysts. And like now, as I told, we have instruments on our booth. It's Raman spectrometers and Raman microscopes. Like now, I suggest the smallest Raman microscope, and for me, it's my favorite parameters of this system is modularity. So you can use a spectrometer and then put it in the microscope platform, so you will have Raman microscope, like system 2-in-1. And this system, as company is young, but nowadays the system already used in different countries, in America, in Europe, in Asia. And most popular applications is skin diagnostics, polymers, geology, forensic, and also guys now suggest instrument for defense analysis, for analysis in the defense industry. So it was a quick overview, as I have only 15 minutes. So if you have any questions, please come to us and we can discuss each instrument in details. Thank you. Any questions?
Who have questions? Okay, I have one small question about heating microscope.
Yeah.
It sounds it's a fantastic story, but what is the maximum temperature, operating temperature of such microscopes?
I think 1,700. I think
700.
Yeah, but
So-
it's something like this, maybe plus minus 100 degrees. I should look at the brochure.
As I understood, it is possible to put materials inside the microscope to heat and to fix the sintering process,
it's
yes?
special.
At different temperatures, yes?
Yeah, and you will see it's like sorry, in Ukrainian сфера, поросфера, то спостерігається процес плавлення кераміки і глазури, і як це відбувається в мікроскопі.
And the change in the structure,
Yeah,
yes? So from the solid to the, for
Yeah.
example, liquid.
And also TA suggests not only heating microscope, it's as we told, a dilatometry platform. It includes a heating microscope and dilatometer and
So we fix
thermometer. Yeah, and process also it's glass. It's the transition in the material. You can look at sintering processes, and so it's like a system 3-in-1.
I want the excursion to your company.
We can send the samples and organize online demonstration with demonstration.
Okay.
It's not problem.
Okay, thank you very much. I would like to remind that after the plenary session, we will have a cover break, and you all can communicate with Oksana, and I think she will answer all the questions. Okay? Okay, thank you.
Thank you.
Okay. We are moving with the conference program, and it's my pleasure to introduce our next plenary speaker. It's, I think, worldwide known scientist, Professor Yuri Gigotsi from Drexel Nanomaterials Institute, from the Department of Material Science and Engineering, USA. Unfortunately, Professor Yuri Gigotsi now is on his way, and there is unstable internet connection in aircraft. So Yuri Gigotsi today in the morning kindly sent us the video recording of his plenary speech, and I think our technical team will record this video.
Good morning, dear colleagues. Доброго ранку, шановні пани та панове. Я дуже вдячний за запрошення be here, зробити доповідь на конференції. Це міжнародна конференція, тому я буду доповідати англійською мовою. Сподіваюсь, що всі мене зрозуміють, і я буду доповідати повільно, щоб було краще розуміти мене. Моє ім'я Юрій Гагоци. Я народився та навчався у Києві, в Київському політехнічному інституті, працював в Інституті проблем матеріалознавства. І сьогодні я працюю в директорському інституті, в Інституті наноматеріалів. Дозвольте мені показати вам свою презентацію. Вона зараз з'явиться. Сподіваюсь, ви можете її бачити. Я зупинився десь посередньо. Але з 90-го року я працюю з
Можеш принести декілька програм стіл поки?
I'm going to switch completely to English to avoid mix-ups at the moment. So today I'm going to talk about a large family of two-dimensional materials, carbides and nitrides of transition metals. Professor Grigory Samsonov from Institute for Problems of Material Science, also founder of the chair of powder metallurgy and metal ceramics at Kyiv Polytechnic, where I studied, is really a founder of this field. Carbides and nitrides were known, but he explored them as materials, published numerous books. And during my undergraduate study at Kyiv Polytechnic, I worked on carbides and nitrides, but bulk structural ceramic materials. Nowadays, we work on two-dimensional carbides and nitrides. They come in a variety of structures. They come in a variety of colors, properties. We discovered them with my colleague Michel Barzum and our student in 2011. And now these materials move really to the stage that they can strongly affect the technology. Even so, I'm working in Philadelphia in the United States. I keep affiliations with Ukrainian universities. Particularly, I'm pleased to have an honorary doctorate from Institute of Materials Science, but also I'm affiliated with Sumy State University in Sumy. And we keep working, and actually just now are submitting another paper with colleagues who are studying vaccines for biomedical application, despite the war, despite a very difficult situation around their city. Now, for people who may be less familiar with two-dimensional or nanomaterials, they're really becoming building block for modern technology because of very diverse electronic properties, from metals to semi-metals, semiconductors to insulators. They have atomic thickness and they're 2D. We can basically build out of them, put them like bricks in the wall, can put organic molecules as mortar or another 2D material. And of course, they offer large surface area. This is a CNN journal of the American Chemical Society that put a cover story about MXene last year, very good introductory reading. So I look at those materials as building blocks for future technology, not only MXenes, but graphene, which was the first one to be separated from bulk crystals, but boron nitride, transition metal dielectric even clays. They're already 2D particles were delaminated and where they can be used as, again, bricks in the wall of new materials. And this will allow us to create materials with a combination of properties no single materials can have. We all studied metals, ceramics, polymers, and each of those classes of materials has its strengths and weaknesses. Here, we can combine properties of different classes of material into one material and do things that no other material can. And MXenes are a large family. We discovered them in 2011. They're not new anymore. You see, there are many books. I just took a selection from Amazon. There are definitely many more. I edited 2 books myself or with my colleague, my former postdoc, Babak Ansori. So there's a lot of reading. This handbook of carbides and nitrides is a good introductory reading and available in Europe as a PDF file for free. two of my former students wrote this book here. Now, to introduce them a little bit further from standpoint of chemistry, we have 2D sheets with 2 to 5 layers of transition metal. From M2, which is M transition metal, X carbon nitrogen can be substituted by oxygen, and T surface terminations, because metal atoms, which as long as those are not noble metals, will never stay non-terminated. So if we look at just a dozen of transition metals, multiply by carbon nitrogen, by 4 structure, we get 96 possible compositions. Multiply by a dozen of surface termination, we have over 1,000. But we can make carbon nitride, oxynitride, oxycarbide. We can make solid solutions. And they were predicted, including by our group, a while ago, but made by Chinese colleagues last year, lanthanide vaccines. And this is certainly just the beginning. There'll be more coming. The first discovered in titanium-32 was reported in this paper in Advanced Materials in 2011. As of last year, there were about 50 MX phases, not counting surface terminations. More than 50 solid solution. At surface termination, you end up with a couple of hundreds of materials. And we did thermodynamic calculations with a colleague of mine, Yonji Hu at Drexel, to show that there are many stable blue structures and many more metastables. So which means that they can exist, can be made, and many of them have been made, structures in this system. And this doesn't account for solid solutions. Moreover, we can not only make a large number of materials, we can truly do atomistic design. We can mix and match, of course, make a solid solution and a high entropy vaccines. But we can also make materials with alternating atomic columns of different elements, or HOA, one of them, for example, scandium, from scandium tungsten carbide, and make atomically thin trenches, or make out-of-plane atomic sandwiches, which have one transition metal, for example, chromium or moly on the surface, another one, for example, titanium in the middle, and so on. And people have already shown many other materials, and of course, surface terminations are very, very important. We mark them with this letter TX, terminations. And people make now silicides, borides, ambients, and other similar materials. Moreover, the number grows very quickly. Just like about a month ago, on September 4th, we published with colleagues a paper in Science reporting 40 vaccines. 36 of them new, solid solution with up to 9 transition metals in the structure. We made max phases, precursors, where aluminum layer connects layer of carbide and transform after that to vaccine. You can see here a picture of a crystal about 10-15 micron length, 7-8 micron cross section, and it has 9 different transition metal elements. Imagine 9 elements in a 1.2 nanometer flake. What is this M4C3 structure is when you transform it to vaccine. So really, we can have 4, 5, 6, 7, 8, 9 transition metals. And what is amazing, we also found that unlike in bulk materials, we're starting with 4 metals. Typically, there is entropy domination and the alloy becomes random. We need to go to 7 elements to ensure that the atoms will be always uniformly mixed. Because a smaller number of atoms, there will be some atoms that prefer to be at the surface because not all layers in such a small structure are equal. And some other elements that prefer to be in the middle. So again, we gain understanding how to design new materials and of course, look into their properties. And you can see a magnified image and EDS map of these materials. Crystal looks like a heart in this case, and you will see 9 different elements present. I find this quite amazing because we truly enter a new era of designer materials. We don't take whatever is given from Earth or nature. We design materials with desired composition and structure. Moreover, we can, of course, combine these materials with other 2D building blocks. Now, I've been talking a lot about how many materials we can make, but let me go back and tell you how we make them. Originally, we took layers of max phase. Max phase is a layered ceramic discovered by Novotny and others in Austria in 1960s, but developed by my colleague Michel Barzum into a class of materials in the beginning of the century, end of last century. What is important? In this layered structure, there is strong chemical bonding between A element like aluminum or silicon and M element of the carbide and nitride layer. As a result, one cannot just mechanically easily break it and make 2D flakes, unlike graphene from graphite or moly disulfide from molybdenite. We have to etch the way, do selective etching, something I've been doing in my lab since my postdoc in Japan in 92-93, where we were removing M atoms from carbide structures to make porous or layered carbones. Now we remove only one element, A element. And there are many ways to do it. We initially use HF, but one can use, for example, hydrochloric acid with fluorides, one can use ammonium hydrofluoride, and there are other ways to do it. But one can also use halogens, gaseous halogen, chlorine or its compound. One can use bromine. One can also make materials by chemical vapor deposition. In case of wet chemical synthesis, we will get a material which can be fairly easily dispersed in water. Single layer flakes, about 7-8 liters, my students is holding here. But in case of halogen terminated MXene, it's more difficult to disperse them, and the material will be hydrophobic. So you see, surface chemistry also play a strong role. And we can make significant amount of materials. We use reactors developed on campus of your institute for Problem of Material Science by my brother's company, Material Research Center, Ukraine. Those are a couple of different models, which allow us to produce significant amount of materials, let's say 100-gram batches. And this is a 1 kilogram of material one of my students is holding in her hands. Thanks here. So the process is scalable. It's very important because it means that we can use MXenes potentially in many applications. Moreover, just a bit 2.5 years ago, Professor Tolapin's group published this very important paper in Science reporting on synthesis of titanium-2 CCl2 MXene by reacting titanium tetrachloride with titanium metal and natural gas or carbon, forming MXenes. And very quickly, less than a year afterward, a Chinese group published fluidized bed process for synthesis of large quality of MXene from titanium chloride. Why it's important? Titanium chloride, when produced by the chloride method from ilmenite, intermediate product is titanium, is an intermediate product basically for making titanium or titanium metal as well. So what does it mean? It's a cheap, available in very large quantities. Ukraine used to be one of the largest manufacturers of titanium materials. So the result, again, we can make large amount of materials by many methods, but you cannot beat taking, for example, natural gas and titanium chloride, reducing it slightly, and making two-dimensional flakes in pretty much any quantities here, because 3 million tons of titanium were produced in 2023 by Chinese scientists alone. So definitely we can make similar amount of MXene. What is also important when we talk about introducing new materials, it's availability. Fight for natural resources is a very serious one. This is definitely one of the reasons Russia is trying to still conquer Eastern Ukraine, which is rich in many resources. When we have materials which are abundant, titanium, aluminum, HTV or silicon, carbon, nitrogen, oxygen in the lattice on the surface, we can make large amount of material and eventually in sustainable way. But when we work with very rare material like osmium or platinum or tellurium, it's very difficult to do anything large scale because they will always stay expensive. Just in titanium system, we can make many, many materials, and I'm not even showing surface terminations, only one solid solution. So we can make really potentially inexpensive materials as the economy of scale starts working. And of course, again, I'm referring to the same Materials Research Center and Carbon Ukraine, both companies founded and run my brother, Dr. Alexei Gagotze. They have been making those materials in Ukraine for quite a while, selling them around the world, both MaxFate precursors and Maxine. So if there is interest, there is a local source of material to acquire commercial material. They have a license from Drexel University. Now, it's great to be able to produce almost infinite number of new materials. Wonderful. If we can make them by scalable methods and have at least a dozen of different ways to make them. Directly from elements, by selective etching, gaseous etching at high temperatures, molten salt etching, wet chemical etching at room temperature. But Maxines will only make an impact if they offer some important properties. If you get a new material with properties that already current materials, say graphite, graphene, molybdenum sulfide, or clay have, the interest is purely scientific. Okay, new chemistry, so. But one of the properties I already stressed is electrical conductivity. Maxines are high electric conductors, which is not new, definitely for people who worked on carbide nitrides and know that carbide nitrides of transition metals have high metallic conductivity. Moreover, they are more conducting and stronger than any solution process to the materials, including graphene oxide, including reducing graphene oxide, about an order of magnitude more conductive. Moreover, we can work directly with Maxine flake. Those are optical, this is an optical image of titanium 3C2 flakes on a silicon wafer. You see large 20 micron flakes, no surfactant needed. You don't have to remove surfactant, unlike when you use metal inks or carbon nanotubes to make conductive traces, films, coatings. And this is by itself very unique combination. But they also come in a variety of colors. Plasmonic, we can make electrochromic systems out of them, change color on demand by applying small potential. Many of them are highly biocompatible, same titanium carbide Maxines. So we can use them in biomedical applications. And they also provide very efficient light to heat conversion. Some other actually reflect IR radiation, making IR stealth materials, and many, many other properties available. Now, what is also important, we can disperse Maxine in pure water, as I mentioned. So we start with ceramic powder, we etch it, make something called Maxine clay, and then disperse in water. And because of high negative surface charge, the potential of Maxine flake stays stable in water. There's repulsion between the flakes. And we can disperse them. You can see different colors of 3 different Maxines. And depending on how concentrated is the solution, what is the flake size? We can make materials for example, inkjet printing or spray coating that flows relatively easily. Or we can make very viscous materials to draw fibers or produce coatings by doctor blading or screen printing. Just by changing flake size and concentration, again, no additives needed, which is very important for processing. And as a result, we can make very thin films and very strong films just from water. Here, my students, Dr. Blade, basically spread on the surface and dried slurry of Maxine that I showed you in the previous slide, highly viscous solution. Now she's removing it from the PVDF substrate. This is a 1 micrometer thin film. It's stable. It's actually mechanically strong, has strength of aluminum, and highly conducting. Just simply spread solution on the surface, you get film, which is strong like a metal, reflective like a metal, and much, much thinner. And that will be important when I talk about some battery applications. And this high strength of MXins allows us to make those films, but also if one just simply takes two-dimensional flakes, mills them, mixes and presses. Tungsten disulfide, moly disulfide, boron nitride give you very low strength value. So 60, 70, 90 megapascal. Graphene oxide a bit stronger, about 140, 145. MXin is about 5 times higher, 660, compared to graphene oxide, and 10 times higher compared to digital carbonides, for example, or boron nitride. That's a very important property because we can make ceramics basically at close to room temperature. Moreover, this is not the limit. When one combines MXin with graphene oxide, reduces graphene oxide by HI and cross-links MXin and graphene by organic molecules, one can make at room temperature material with mechanical strength, tensile strength, higher than steel. Imagine at room temperature from solution, getting film on the surface, treating it slightly, and getting stronger than steel material. But this material can also conduct ions. So it's so known ionotronic material. Conducts electrons and conducts ion. We can use it as electrochemical actuator, change shape and change color by reducing oxidizing MXin surface, uses electrochromic, and it's strong. We can make robots, we can make many other things here. And no metal can have ionic and electronic conductivity at the same time. So it's stronger than metal and has properties that metals don't have. This is what I talk about when I talk about assembly of new materials from two-dimensional building blocks. Now, what's also important, all these properties are tunable. By changing density of state, basically amount of free electrons available, we can change conductivity, eventually even opening the band gap was predicted. You can change work function. You can tune work function for solar cells, OLEDs, light emitting diodes, organic, for flexible electronics, flexible energy harvesting we develop, combining flexibility and high electronic conductivity and tuning the work function to optimize performance of devices. And that's an example which is usually given as the first example of human-made nanotechnology. The Roman cup from Roman Empire, which is stored in British Museum. It is red in transmission, just like titanium carbide, green in reflection, just like titanium carbide, titanium 2C. But unlike titanium carbide, it's achieved using gold and silver. And we can do it with abundant elements. But if you add a little bit more, one layer of titanium extra, one layer of carbon, and go to titanium 3 the absorption peak will shift to 780 nanometers. And this material will become green in transmission. So you see how we can control the properties of this material. Now, research is going over the world. This data were assembled probably about this time in 2024, published in December, so a year old by PetSnap, patent analysis. Close to 10,000 patents were filed at that time, definitely more than 10,000 nowadays. China, South Korea captured the lead in the field, just like in many other materials field. And MXins have been pronounced by in the International Union of Pure Applied Chemistry, IUPAC, among top 10 emerging technologies in chemistry last year with a true potential to transform our world. So, to transform our world, what do we need? We need killer applications. We need to find applications where these materials can make something other materials can. I gave you a few hints already. Making flexible displays and solar cells, making super strong ionotronic materials for implants, for other application and control of properties needed. But there are many, many more. We in my group worked on energy storage in the beginning of our glorious path toward the exploration of MXene. We still keep working on battery applications of MXenes, but there is much more beyond batteries and supercapacitors. Just sensor, for example, the fastest growing maybe segment lately, and look how many different kinds of sensors being explored. But this goes to tissue engineering, thermoelectric, thermocommunication, infrared styles, and many, many other things. Let me give you just a couple of examples. Why MXenes are attractive for energy storage for basically batteries, lithium, sodium, magnesium, aluminum. They're 2D materials. There is no solid state diffusion that can be charged quickly. There are interlayers where ions can move without being slowed down by bulk diffusion. But it's also important to have very high conductivity. This plot is called Argoni plot. It shows specific power, so how quickly battery can be charged or discharged, versus specific energy, how much energy we can store. And you see, conventional batteries store much energy, but rate is not high enough. Supercapacitor, double layer capacitor, store much less energy, but can do it faster. What we're looking for are materials that can both store a lot of energy because of redox processes, and titanium, moly, niobium, vanadium are exactly the metals that are used in current batteries, but also do it faster. And say titanium 332 has 2 to 3 orders of magnitude high conductivity compared to the highest, fastest devices for energy storage, activated carbon or carbon-derived carbon made supercapacitors. So that's why there's so much interest. And we can design the surface for different electrolytes. We can actually work in, say, chloride electrolytes, aqueous chloride electrolytes, which metals can tolerate. And there are many other advantages, including dendrite suppression. But I wanted to mention just one. Say Ukraine uses drones a lot. And drones require energy storage. If you use an electric motor, quadcopters, for example, you need to power it. Weight is absolutely critical. 6 to 10 micrometer copper foil is used as current collector in lithium-ion batteries with graphite. We replaced it with a 2 micron current collector made of titanium 332 MXene using 130 micron commercial type of a thickness commercial material, graphite. We got close to 1/3 saving for the anode in the weight. And also we shaved off about 10% of thickness. You can imagine how important it is for this type of devices, making it 30% lighter, 10% thinner. So those type of applications that can be enabled by these new materials here, but of course there are many, many others. One can replace conducting binder and conducting additive at the same time with MXene instead of carbon black, nanotubes, and PVDF. There are many other possible applications. We can also use MXene wherever low weight is needed and electrical conductivity. For example, instead of using metal waveguides, which are on all flying objects needed for radars and planes or satellites and so on, we can replace the metal one with a polymer printed, various shapes, pretty much any shape, much easier to make. Just by dipping into MXene, we'll get material which is conducting 10 times lighter, not now 30%, but 10 times lighter, about 10 times less expensive to manufacture. And they can work to basically make satellites lighter and save a lot of money on sending heavier stuff to space. MXene also interacts strongly with optical radiation from X-rays to microwaves. And there have been many applications explored from photothermal therapy to terahertz and gigahertz antennas electromagnetic shielding. For example, in electromagnetic interference shielding, titanium carbonide MXene shows better shielding compared to metals of the same thickness. Again, lighter, thinner, and better performance. This is reflection, protect electronics, and so on, from jamming, from noise, electronic noise in device. But we can also use another MXene, vanadium carbide, to have very efficient absorption of electromagnetic radiation. You see again better than other materials people study. I already mentioned the importance of work function tuning. This is a work done together with our Korean colleagues. They wanted to use MXene as electron transport layer to replace so-known ITO, indium tin oxide, which is brittle and breaks when one bends OLEDs, but the same is true for displays of foldable cell phone or rollable foldable solar cells. They made a 10 nanometer film from our MXene on the surface, and they not only make it flexible device, but the luminance, brightness, and this logarithmic scale increased by almost an order of magnitude. So it became brighter and can be flexed now. So I think this is again where 2D material bring novel applications here. And another one is related to insulation and infrared properties. If you look at thermal conductivity versus electrical conductivity, Weidmann-Franz law suggests that if material has low air emissivity, it must have high thermal conductivity, high electrical conductivity, and vice versa. So no materials but MXene were able to get into these patterns in diagram. As a result, titanium carbide MXene coating provides much smaller heat loss from the surface because it has low conductivity across the layer and low emissivity from the surface of the layer, like in a polished metal. And of course, as usual, these properties vary of composition. Titanium 333 is very low emissive material. Niobium 2C will be a highly emissive material. So we can cover a broad range of emissivity values and select the material we need. But what is important? Very thin film of MXene can drastically drop the temperature. Blue means cold when you put a sample on a hot plate and take a picture with the video camera. And we took 3 different MXenes. As you see, there is big differences. Put them on a 120-degree plate and heat it for 5 minutes to stabilize the temperature. What we will see, a 200 nanometer, extremely thin film, extremely thin sub-micrometer film, pretty much drops temperature by 80 degrees. Imagine coating walls of every building, every room in MXene, how much energy you can save. Industrial equipment. So heat losses can be modified drastically with extremely thin layer of material and make potentially clauses that will allow one to be flexible, wear comfortable clothes instead of very thick scaphanders, and say walk on Mars, Moon, or Antarctica wearing thinner but better thermal insulating clothes here. And just to demonstrate this, my student washed a MXene short in washed a white cotton short in a dispersion of MXene flakes, and you can see IR camera. With MXene surface, the short temperature remains almost close to background temperature, while the conventional white short, even so white reflects heat, accept temperature close to body temperature. So a person can become invisible and feel much warmer because much thicker thermal insulation can be replaced by very thin layer of material. There are many other applications. The biomedical application of MXene are growing very quickly. This is where we work with Professor Maxim Pogorelov and his team from Sumy State University. Very wide range of possibilities in that field, from anti-cancer therapy to wound healing and medical diagnostics. And I would like to finish showing one example only. Working with our colleague at the University of Pennsylvania across the street from Jacksonville, we showed that titanium carbide maximum epidermal electronics, electrode on skin for electromyography, measuring muscles movement, electrocardiography, encephalography, greatly outperform commercial on lab-made gold and platinum electrode. The signal to noise ratio, you see, intensity of the signal is much higher compared to gold. And it's not because titanium 332 is more conductive. It's not, it's less conductive. But the impedance the skin is lower. Because of this hydrophilic surfaces, it adheres nicely to the surface. And the barrier for electrons to overcome becomes smaller. We get smaller intensity. We can also record ionic currents and don't require gel, unlike metal electrodes. And more comfortable to wear when you wear it, for example, on scalp for encephalography for a long period of time. So this is an application on the way to commercialization. And of course, it will take longer to make implantable electrodes, but it beats greatly graphene in terms of conductivity and processability, and outperform gold in terms of contact resistance or impedance. So I think it's a great application for MaxSim. Many other fields, people talk about maxitronics, electronic based on MaxSim. Composite materials. MaxSim have great properties, but one can incorporate them in polymer, metal, ceramic matrices. Further controlling the properties, aiding conductivity or electromagnetic interference shielding to ceramics and polymers, reinforcing metals without losing strain to failure. There are many very interesting applications for MaxSim. It's time for me to wrap up and finish here. So I would like just to mention that in my group, we discover, develop, and tune MaxSim. We study some of the properties, but no one can do everything. It's very important that if you have a certain background, you can look at this emerging family of materials and ask yourself, where can we use them? Where they can help you to solve your problem, replace current materials, enable something that cannot be done by any other material. And I think this is a direction the research community should take nowadays with MaxSim. Look at them as enabling materials that will allow us to build future technologies impossible with conventional bulk materials today, and don't hesitate to combine them with other materials when needed. With this, I'm going to stop. Thank you very much for your attention. Unfortunately, I won't be able to take questions online, being in the air during the time of this talk. However, you can go to my group website. You will find my email address if you want to ask questions. You will also find many presentations on our YouTube channel. You will find copies of our papers and a lot of other materials. So if you have questions, please don't hesitate to contact me. And with this, thank you very much again for listening to my talk. I hope Samsonov's tradition of developing carbide, nitride, and borides will continue at Institute of Product Material Science and in Ukraine in general, now making two-dimensional, low-dimensional materials from these compounds, which were to a large extent developed in Ukraine. Дуже дякую. До побачення.
Okay, as Professor Yuri Gogodze mentioned, unfortunately, we don't have opportunity for the discussion, but I would like to note that Professor Yuri Gogodze has supported us for many years, supported the Francevich Ukrainian Materials Research Society and all our conferences, and we are very thankful to him for their support. Not only for the today lecture, but for his overall support. Thank you very much. And now we are moving with the conference program, and I would like to invite our next speaker. It's Alexey Milenin. He will present the project Knowledge of Rice from Kyiv Academic University and Academic City. Yes? Okay. Your floor, please.
Just a minute. 111 222. 1. 1. 1, 2, 3, кажуть. Державною мовою має запрацювати. О, є.
Оп.
Раз. Okay. Good day, colleagues. It's has already become a nice tradition for our international consortium to participate and to help in the organization of conferences that is organized by Institute for Problems of Material Science. So, and my today brief presentation concerns our novel initiative, Knowledge Rights Project. That is held within the framework of initiative of European Institute of Innovation and Technology. And this project is closely aligned with the trends and demands of HighMatTech initiative, which intend to engage universities, academic institutions, innovation organization, and others to deep tech topics. And our project will try to make a bridge over the gap between education, innovation, and entrepreneurship. Of course, this is ambition. Aim is rather ambitious, but I think with our colleagues, with our partners of international consortium, will be possible to make this project success. And if we talk about Knowledge Rights Project, there is a very successful precondition of this initiative, Boost Talent Project, that was finished this year. And this is, I think, a rather successful result of our cooperation. This project is the same in the framework of European Institute of Innovation Technology, but it's mostly educational one. Here we create unique educational program that reflects the main topics of deep tech, and this educational program is modular and consists of a number of short-term courses read online and divided depending on them. Initial point, our participants, our students, and everyone could build up his own educational line. As an examples, the topics of these courses, the basic courses, intermediate, and advanced. Moreover, the Boost Talent project is over, but now we have opportunity to involve students to pre-recorded lectures. The results of implementations of the project is several hundreds of participants, and they pass through our educational program gain certificate, and not only numbers shown the impact of our initiative, of our activities. Last year, Kyiv Academic University, that is the Ukrainian partner of this consortium, was gained Trainer of the Year in Deep Tech in Europe, awarded by Institute, European Institute of Innovation and Technology, and initiative. So again, this program is available on the Kyiv Academic University educational platform. You can find there pre-recorded material. Moreover, 5 courses were certificated by European Institute of Innovation Technology, and now is a part of their European education platform, and among other well-known and honored materials. So you can see that Knowledge Rise have a great foundation for its beginning, and it's not only the use of our experience, but the next step. Knowledge Rise is more mentoring project that combines 3 main pillars of our activities through connection of fundamental knowledge, educational part of this program, innovation and entrepreneurships. This was implemented in view of Deep Tech Interdisciplinary Educational Initiative that is open now. We choose 6 main directions of our activities. This covers main topics of Deep Tech. It's AI, ML, it's advanced materials manufacturing, additive manufacturing, green hydrogen transportation, quantum materials, and innovation management. And you can see that it begins with the same short-term educational courses that will be held in October and November this year, so you can participate in them. And then if anyone have its own ideas or innovative teams or startups, you can join innovation phase, where we will provide mentoring for providing innovation activities up to some commercialization and entering entrepreneurship phase. So I think everyone who have its own ideas, especially we talk about the young scientists, or if you teams need the help of experts for mentoring, especially for some research-based initiatives, startups, you can find the help here. Briefly, what are the lectures, what are the courses we will start this autumn? First of all, it's advanced materials manufacturing. Here you can find the information, the knowledge about how the advanced materials are produced and what are the main technological principles, innovation principles. Quantum and nanomaterial science presents, provide them some knowledge about the fascinating world of quantum effects and how they could be used in practice. 2 very important topics and combination of AI and additive manufacturing, and how the use of AI and ML to optimize or develop additive manufacturing technology. And very also rather important for us topic is energy transition and the role of hydrogen transportation in there, and combining of material science and corresponding consequences to engineering implementation. So it's very briefly, and everyone who listens to these courses online will gain corresponding certificates with credits, EKTS, and training hours. Moreover, this all free of charge. The only thing you need is to register on our platform, Kyiv Academic University or Academic City. I leave in the whole corresponding materials where you can find all needed information for that. So, in conclusion, I think, first of all, I wish all of you successful conference and wait for you in our current initiative and look for our other initiatives. I think it will be useful for all of us. Thank you for your attention. I could answer all questions here or during coffee break.
Thank you very much. Are there any questions? No, but I have one remark. So today, I know that we have some PhD students in this conference room. So, dear PhD students, I know you are here and you still have time to register for this course. I recommend. Okay, thank you very much.
Thank you.
Dear colleagues, we are finalizing our plenary session, but currently I am kindly ask you to join us to make the team photo of all participants of the conference. Currently, I am inviting all of you to go to this stage, and we will have the team photo, and also the our offline locations also will make such photos, and then we will join our offline photos into general photo of the conference. Please go here. Dear online participants, if you, I know you are with us, please, if is it possible, switch on your cameras, and you will be also in this team photo. Андрій Володимирович, товариство, проходьте. Не розходьтеся, всі підходьте. Я не по... Колеги, підходьте всі, аспіранти.
Все из материалов research
Я точно, я така. Я пересяду.
Помните про сын.
Підходьте ближче трошки. Підходьте два ряди, вставайте. Сергію.
Я скажу. Вгадайте про сина.
Щільненько, щільненько. І всі кажемо HighMatTech. Ну, раз, два. HighMatTech.
Давайте ще раз. Раз, два.
HighMatTech. Колеги, будь ласка, не розходьтесь. На дворі чудова погода, чудова природа. Давайте ще на дворі підійдемо перед входом, там гарне освітлення, а потім ми всіх вас запрошуємо на каву на другому поверсі ось тут. Чудово. Дощу немає. Hi, everyone. Dear Olga, are you hearing us?
Just a moment. Is Professor Diplomer online?
Нас не чують? Dear Professor Olga Zverkov, are you hearing us?
Yes, yes,
Okay, can we start?
yes.
Okay, so it's time to start to continue with our conference, and according to the conference program, we are starting work of our symposium, Hydrogen Material Science. And it's my pleasure to introduce the head of symposium, Professor Olga Zverkov from Karpenko Physico-Mechanical Institute, National Academy of Science of Ukraine. Dear Professor Olga Zverkov, please, your floor.
Thank you for the kind introduction, Dr. Solzhenko. Good afternoon, everyone. Dear colleagues, first of all, it's my great pleasure to welcome all of you to the symposium on hydrogen material science, which is organized within the HighMatTech-2025 conference. Therefore, I would like to thank the Armed Forces of Ukraine for the opportunity Okay. Sorry for some technical issues. Are you hearing me?
Yes.
Okay. Okay. I'll continue. As we know, green hydrogen currently plays an important role as a decarbonized energy carrier, and it's already used in various industries. In May 2022, the European Commission presented a new plan to rapidly reduce the consumption of oil and gas and fast forward the transition. However, the development of hydrogen energy and widespread usage of hydrogen in the global energy transition.
Dear almost Virgo,
Yes.
please wait some minutes. We will decide technical problems because we hear you but very poor.
Recording in progress.
Okay.
5 minutes we will say when we can start.
Okay.
What about now? Can you hear it better?
One. Да.
Самому буде подальше USB.
Can you hear me?
Один. Це чути. Пробуйте. І подивіться, щоб воно включилося.
Can you hear us?
Yes.
Oh, thank you.
Okay, it's okay. Now it's okay.
Okay, I think we can start now.
Okay. Now let's go down to start our symposium. We have 2 oral sessions and also 1 poster session on this topic. And I would like to introduce our keynote speaker, Professor Tom DePower. Professor DePower is appointed as an Associate Professor of Sustainability in Engineering with a focus on environmental assisted degradation of metals at Ghent University. Also, he holds on environmental assisted degradation of metals, okay? And he holds an adjunct associate professor position at Curtin University in Australia as well. Before he performed a research stay at the Norwegian University of Science and Technology. His work has been recognized during multiple invited keynote lectures and several awards, including the Hydrogen Europe Research Award in the category Hydrogen Storage and Distribution. The title of the talk is Enhancing the Hydrogen Enrichment Resistance by Microstructural Design. Please, Professor DePower, are you hearing me? Can you share your presentation? Okay.
Yes, I can.
The floor is yours. Welcome.
Thank you. First, to check, can you see the screen and can you hear me well?
Yes.
Oh, fine. Thank you. Then I go ahead.
Yes.
Many thanks, Professor Zirko, for the kind invitation. It's a pleasure to be here today. My name is Tom DePower, indeed. I'm from Ghent University and from Curtin University in Australia. I was nicely introduced by the chairperson. In our group, we focus on 4 different topics when we study metals and degradation. 2 of them are linked to hydrogen. The first one deals with fundamental understanding. So there we always combine a lot of hydrogen characterization, like diffusivity, trapping, solubility, with the microscopic characterization. So in this case, you can see on the left-hand side, left top, a TDS profile, which shows the trapping at specific defects in a microstructure. And then we couple this with SCM, EBSD, TEM characterization to know what is the responsible defect responsible for the trapping. I'll take a look if I can have a pointer. Yeah. Okay, we'll see. And then we have on the left bottom the second topic of our group. So the first one is very fundamental, very much academic oriented, and the second one is much closer to the application. So there we check the applicability of hydrogen gas, and this is indeed linked to the energy transition and the oil and gas sector, as we want to retrofit the existing gas grid from natural gas towards the use of hydrogen, pure or in a blended form. So there the European backbone is quite important. And then we worked closely together with the operator of the Belgium grid to check if their grid can be used for the purpose of hydrogen transport and distribution. And as you can see, we evaluated actual pipelines, heat affected zones and their welds, both electrochemical and in gas environment. And this is the second topic of our group. So these 2 are linked to hydrogen, the other 2 are linked to corrosion. Just very quickly, there we focus on, I'll always call it mild and harsh environment. With mild, I mean seawater context or cooling water context, where a lot of electrochemistry is used and where we go from lab scale to pilot scale to trying to come up with inhibition, for instance, of cooling water. And then the fourth one is linked to more in harsh environment. This can be higher pressures, higher temperatures, the presence of H2S, CO2, and much more aggressive corrosion that we then try to do methodology development in autoclaves or in dedicated cells, combined with a lot of post characterization and also some in situ monitoring of the corrosion happening. Good. Topic of today, we will focus on the microstructure, how we can do some alloy design to make materials behave better. I will start with a general concept on trapping and how defects or discontinuities in a microstructure can affect hydrogen transport. And then I will show you some examples more linked to the applications. So let's start with the generic concept, and this is linked to the addition of carbides. I think we all know that carbide addition can be interesting to trap hydrogen and to make sure that the fusible hydrogen does not go quickly to the crack tip, leading to fast propagation of the crack. Well, if you take a look in an electrochemical environment, I hope you have seen that. I will show it again. There it goes. In an electrochemical environment, you do it at room temperature. This means you'll give little energy to the atom of hydrogen to diffuse to the lattice of a metal. And then typically, if we add a carbide into a microstructure, we have the interface of the carbide with the matrix, but we also have the carbide bulk, for instance, the vacancies within a carbide. We know if we charge at room temperature that we are able to charge the interface of the carbide with the matrix depending on the coherency of that specific precipitate, but not the bulk. So we don't go inside the carbide. This has been verified with some atom probe analysis, and you can see that the trapping barrier, ET, the trapping barrier is too high to overcome. And that's why we don't go inside the bulk. So if you take a look again to the green atom, we don't go into the inside of the bulk at room temperature. But if we then modify and we go to higher temperatures, and in the electrochemical environment, this case you can do it up to 80 degrees, but then you start boiling. So then we go to gas environment, and then it's different. Because then we can have enough energy to overcome that barrier and we can go into the interior of the precipitate. And this is a much stronger trap site. So this is important that an atom has some energy to travel through the lattice. And I'm very much convinced that this is not only temperature dependent, but also load dependent. So that the stress also affects the trapping ability of the microstructure to hydrogen. Here you can see some example of a fundamental study where we have some iron carbon titanium alloy on the left hand side as quenched. So we only have trapping at the martensitic matrix. If we then do some tempering, we go to the QNT condition, we induce tempered induced precipitates. So we have titanium carbides, and we can see 3 additional peaks linked to the trapping of hydrogen at the interface of carbides with the matrix. It's the interface because we are still at quite low temperatures. And at the interface, we have misfit dislocations and carbon vacancies, and they're responsible for the trapping at this interface. This has been nicely shown as well in the pioneering work of Takahashi on the atom probe, where the deuterium segregation is found to be linked to the titanium carbides present. So this is electrochemical room temperature. And why do we do this? Well, we want to make sure the resistance is higher. So if we now take a look to this tensile testing, so we did some S-quenched tensile testing on these materials. We had an embrittlement of 53%. If we go to QNT, so we fully charged, so it's completely full of hydrogen, we have worse performance, 66, and this is because we have more hydrogen in the sample. So it's not a fair comparison. But if we have this QNT microstructure with the carbides, and we charge that microstructure with the same amount as the S-quenched, so the 53, then we only go to 23% of ductility loss. And this is showing the beneficial effect of carbide addition. Why? Because hydrogen easily goes or has a higher tendency to go to the deeper traps. So there you can see 2 spectra, one linked to a lower time, and then you can see that the deeper traps, so at higher temperature, is first filled, and if you then continue, then also your lower trap sites will also be completed with hydrogen. And this is showing your resistance. And this is also quite important. Here you can see if you don't go to saturation, so only in situ for a temporary exposure, then the addition of carbides is beneficial because it can shield hydrogen to go to critical regions. But if you fully charge a sample, so full of hydrogen, first the carbides will be filled because they have a stronger interaction with hydrogen. But after a while, these carbides will be full, and then also your weaker trap sites, grain boundaries, dislocations, they will also be trapped by hydrogen. And then it's no longer beneficial to have the carbides. So there you have to check your application. If you're going for instance, corrosion or a temporary exposure of hydrogen, then carbides can be interesting because they can take hydrogen and they can trap it quite deeply, and then it is prevented to go to dislocations or to weak spots in the microstructure. But if you have continuous exposure, as in the case of oil and gas applications, where there's a constant environment of hydrogen, then the addition of carbides is no longer interesting. That's the first step. And here you can see, so this was done electrochemical. If you do it gaseously, so then you go to higher temperatures, then you can go into the interior of the carbide. And then you can see the spectra that you can see on the left bottom. There you can see that hydrogen is trapped at much higher temperatures. And this means we go inside the carbide. And then some beautiful DFT work was done by Di Stefano, his group. And there you can see, depending on the vacancy structure in the carbide, being isolated vacancies or connected vacancies, we can have a different spectrum of our TDS. So this is an introduction to the topic, that we can tweak microstructures, that we can change something in our microstructure to make the material behavior better. Let's now have some case examples. We will start with a bearing application. With bearing, we mean very high strength, low ductility materials. And there we're going to try to optimize the performance in presence of hydrogen. This was done in close collaboration with the Max Planck Institute for Sustainable Materials in Düsseldorf and Professor Springer. Here you can see that we are working with an iron carbon material, but in one case we added some aluminium. So you can see we have an iron 0.4 carbon material. And then when we add 2 weight% of aluminium, you can see that we shift the ferritic nose, so the green ferritic nose, to the left top. It means that upon quenching, so it's a quenched material. We go through that ferritic nose and we produce some microfilm, a ferritic microfilm on the prior austenite grain boundaries. And this is shown in the SEM micrographs at the bottom. So there on the left-hand side, you can see the iron carbon material, so fully martensitic. But if we then go at aluminium, you can see that at the prior austenite grain boundaries, there is this black, and we thought in the beginning perhaps open space because of quench cracking. But if we zoom in and we do some ECI analysis, we can nicely see a dislocation structure at this microfilm. And this is linked to the presence of a BCC ferrite phase at these prior austenite grain boundaries. And this is linked to this crossing of the ferritic nose upon quenching at 220 degrees per second, as you can see in the graph on top. If you further take a look into this, so we go to TEM, then you can nicely see this martensitic microstructure on the left top and the right bottom. But in between, in region E, this is the ferritic microfilm. So there you can see that with some diffraction, so we have some nice BCC present. And also you can see in green you can see the carbon distribution by EDX, and you can nicely see a depletion of carbon in this ferritic zone. So what happens upon quenching, your carbon is pushed towards the surrounding FCC because of the high solubility and FCC of carbon, and then we quench it down. So our martensitic microstructure has a lot of carbon, but at the prior austenite grain boundary, we have some nice ferrite present for 250 nanometers, so a very tiny microfilm of ferrite in the microstructure. So this is one thing that is changed with the addition of aluminium. So let's take a look then to the mechanical performance later on. A second thing is that when we temper, with the addition of aluminium, we also delay cementite formation. So if you do a tempering at around 250, we can see that for, we can see that for the green, for the green material, we have some cementite. So if we don't have aluminium, but if we have aluminium and blue, we see that the DV delay. So this is a DSC graph. So you can see that the peak of cementite formation is delayed towards higher temperatures. So if you only temper at 250, 275, you have cementite in the case without aluminium, but there is no cementite in the case with aluminium. And these two conditions, these two tempered conditions, they come with equal hardness, equal dislocation density. So that comparison allows us to check the possible trapping of cementite without a change in dislocation density or other factors. So let's now take a look to the results. So this is without hydrogen. So this is iron 0.4 carbon. And then we can see that we have almost double or more than double the ductility if we add aluminium. And this is without hydrogen. So this is an air test. And this is a bending test. Why? Because we're dealing with very high strength, low ductility materials. And when we add hydrogen to those materials, so this is linked to the bearing application, they fail before yielding almost. So they have subcritical cracking because of their high strength levels. And that's why we need to go to bending mode to increase or to have some plasticity on our materials to check the performance. If we take a look to the fractography, we can see that without aluminium, we have nice intergranular type of fracture. And with aluminium, we have the same type of fracture. You can see underneath the dimples, you can nicely see the intergranular type of fracture, but you can see on top a nice layer of dimples. So this is the ferritic microfilm that was ductile and that was deforming and that was acting as a glue holding the structure together. And this is why we increase ductility with more than 100% if you go from red to blue. And the nice thing is that we don't compromise in bulk hardness. Both materials have a bulk hardness of 580 HV, more or less. So we still have the same hardness value, but locally we increase ductility because of the presence of this ferritic microfilm. Of course, if you go to nano-indentation and you go to local hardness measurements, you can see the drop in hardness at the ferritic microfilm. That's quite logic, but the bulk hardness, that's still equal. If you zoom in a bit more, we have some beautiful pictures that you can see this intergranular type of fracture underneath, but on top you have nice dimples of this 200 nanometer layer of ferrite that act as a glue and is ductile, deforming upon bending the sample. Let's now take a look to the presence of hydrogen. What is happening then? Well, without aluminium, we go from intergranular type of fracture to a quasi-cleavage mode, which is shown in the green arrows. So it means that the propagation of failure is along the packet and the block boundaries. So this is the weakest path in this material. But if we add aluminium, we keep on having intergranular type of fracture. We don't go to the quasi-cleavage type of fracture, which was in this case, for these materials, the worst mode of fracture. So the microfilm, the ductile microfilm, is redirecting the crack propagation from the packet and block boundaries to the plied austenite grain boundaries when we add aluminium. And in this case, we also optimize the ductility in the case of in the presence of hydrogen. So we change the mode of fracture because we have modified on a local scale or microstructure. The second mitigation was the addition of cementite. So as you can see in the TDS profile, so hydrogen versus the temperature, you can see that the cementite is present at the highest temperature. So it means if you start charging and you have equilibrium with your lattice and your traps, your cementite will be first filled in equilibrium, and then it continues with time to high angle grain boundaries and dislocations, which are at the lower temperature scale. If you then take a look to the bending results, we can see that if we fully saturate the samples, and this is the full lines, that we have upon tempering only there's the same increase. So that's not playing a lot of effect. But if we do it in situ, and this means we don't go to full saturation, but we do the test together with the charging, and hydrogen can enter the microstructure together with the bending load which is applied, you can see that the case with iron 0.4, in that material we have cementite. As you can see also in the TDS, there is cementite. And then we have an increase of 53% of ductility if we do this in situ testing with a tempered microstructure. If you do this with aluminium, then you don't have any cementite, and then your increase is only 16% when you temper. So that's not playing a beneficial role. And this is all linked to the fact of in situ charging. If you do in situ charging, it means your hydrogen is not spread everywhere. It first goes to the cementite, as you can see on the left bottom. Then you can see these orange dots, they represent the cementite. Hydrogen goes there, and you still have intergranular type of fracture with the in situ testing. You can nicely see with the red circles, you can see the cementite particles on top of this prior austenite grain boundary. But if you go to full saturation, then you first charge cementite, but then also your high angle grain boundaries and your dislocations. So you again go, your hydrogen goes to the packet and the block boundaries, as is indicated in the schematic representation of the microstructure. And you have again quasi-cleavage type of fracture as shown in the green arrows. And this is worst performance for these materials. So it's a similar story as for the carbides. Cementite can trap. It's not a very strong trap, and the temperature is quite low, but it's an effective trap, and it can also help with your ductility, because it can retard the accumulation of hydrogen at the weakest pathway. And in these materials, the weakest pathway were the packet and the block boundaries. And this is only true for temporary exposure. So the same story as for the carbides. If you do it for corrosion or some temporary availability of hydrogen, then this is a valid mitigation strategy. But if you do it for oil and gas application, where there is continuous supply of hydrogen, then your cementite, your carbides will eventually be filled, and then also your weaker trap sites will also be filled. So the beneficial effect will be gone. All right, second example, now we go to a collaboration that we did this year with Dr. Torsten Michler from the Fraunhofer IWM Institute. There we checked the perlitic cold drawn steel. So we wanted to make a comparison between the paralytic microstructure, and the martensitic microstructures. And this is for high strength applications. As you can see, we go to quite high strength levels. And now we do gas tensile testing. So 100 bar of H2, pressurized hydrogen. And we compare the martensitic material with the paralytic one. The paralytic one is shown on the right top. It has a perlite colony size of 4 microns, an average lamellar spacing of 0.06, and only 12% of cementite. And then we have the martensitic one at the bottom with a prior austenitic grain size of 13 micron and a packet size of 4 micron and a lath thickness of 0.4. If we then do the mechanical testing, you can see that the black one, the martensitic one, has a lot of ductility loss, very severe hydrogen embrittlement, while the paralytic one, even showing a higher ultimate tensile strength, and normally the sensitivity increases with the strength level. But in this case, the green one was showing very good resistance. And this is interesting because this would mean that these paralytic steels can maybe replace the martensitic ones for hydrogen applications. What is now the reason for this? First, we check the fractography, and here this confirms what we also observe in the tensile testing, that in the left, the paralytic one, there is hardly any hydrogen-assisted fracture noticed, but in the one in the QNT martensitic microstructure, we can see a lot of trends and intergranular fracture. So there, the embrittlement was very, very severe, and we only had a tiny section of microvolt coalescence, as you can see in these fractographs. This is mainly confirming our observations by the tensile testing. What is the reason? Well, perhaps trapping is different. So let's compare and let's take a look to TDS. The paralytic one shows this peak, very tiny peak, but at higher temperatures. And it's a quite strong peak if we analyze it. So we do some deconvolution at different heating rates, and then we can know how deep the trap is. If you calculate this, we can see that peak 3 comes with a desorption activation energy of 146 kilojoules per mole. So this is very strong trap present in the microstructure, and this is not during the test. So this is before testing. My belief is that it only increases upon testing. The same as for the temperature effect, the load has an effect on trapping, and that trap density can increase during your mechanical test. So if you take a look now to peak 1 and 2, for the paralytic one, we have these locations with 27, and then we have strained ferrite cementite interfaces at 33. But we believe, because of the high desorption activation energy, that peak 3 is linked to the vacancies inside the cementite. This is what I was referring to in the beginning in the general introduction. And for the martensitic ones, we have trapping at these locations, the lead boundaries, and again, the high angle grain boundaries. If you want to prove this is now an observation that can explain the better performance of the paralytic material. It's of course not full confirmation. It's not, we have a hypothesis based on this. If you would like to confirm this, you need to go to atom probe. And this is some work that was done by the Japanese group of Shibata, published last year. And then you can nicely see if you deform your microstructure, well, at the cementite, at the strained interface of cementite, if you deform, you have a segregation of deuterium. So if you take a look to the deuterium, so in red, the deuterium signal, you can see at the interfaces on the left-hand side, this is undeformed, then the deuterium signal in red stays quite stable. But if you go to the right-hand side, there we have a deformed sample. Then you can see that at the interface of cementite with alpha, we have a segregation of deuterium. So the red curve is increasing at the interface. So this is pointing towards preferential trapping of hydrogen, deuterium in this case, at the interface of cementite with the matrix. We believe that our trapping is within the cementite because of the high activation energy, but it's only atom probe that will show this. This is a different material. So in this case, they had interface trapping. It might be that we have bulk trapping at the vacancies. So this would be a next step. Good. Then we go to the last two examples. So we continue with the carbide story, but on applied steels now. This is in collaboration with the Materials Center in Leoben, Dr. Volja Razumovsky, and also voestalpine wire rod. Matthew Geller was there in the collaboration. So here you can see that we work with fastener materials. We have a reference material, but then we alloy it. So in alloy B, we have additional titanium, and in alloy C, we have the same amount of titanium as compared to alloy B, but we also add 2000 parts per million vanadium. Both titanium and vanadium-based carbides are known to be beneficial or possible traps for hydrogen. We see on this fractograph that we have radial cracking, which is a phenomenon that leads to extra plasticity and is basically preferential for the plasticity. Let's take a look now what happens with hydrogen. So in alloy A, this is without the additional titanium and vanadium, we lose radial cracking in the presence of hydrogen. This is ex situ testing. With ex situ testing, we mean fully charging. So the sample is full of hydrogen, but the test itself is done in air. So it's ex situ, and this is interesting in certain applications. It's always a question if you need to do pre-charging, ex situ testing, in situ testing, not pre-charging. Well, it depends on the application, a bit what you want to evaluate. So in this case, we compared both to have both methods. And now we can see that we still have an alloy B and C radial cracks present, and this is linked to the increased density of carbides. So we have more titanium and vanadium-based carbides, and this is the initiation of these radial cracks. If we add hydrogen, we still have the radial cracks. So this is beneficial. If we then calculate the hydrogen embrittlement index, it's interesting to focus on the necked area because the phenomenon of radial cracking is only happening from UTS onwards. So it's a necking phenomenon, and this is leading to a quite extensive necking area. And if we then zoom in on that specific region to calculate the index, we can nicely see that we have a much better behavior if we have carbide addition. Not because of trapping, but because of provoking radial cracks, also in the presence of hydrogen. If the carbide content is too low, as for the case of aluminium, your radial cracks were no longer happening in the presence of hydrogen. So this is the first thing. And then we also went to in situ testing. And in situ testing, you have an environment of hydrogen. This can be electrochemical or gaseous, but then you have edge cracking, secondary cracking. And this is interesting if you want to check, for instance, acidic stress corrosion cracking, because that's also a surface effect. And in this case, because of the side cracks, your necking area is much more refined. So you have a much lower neck zone and no more radial cracks can develop. So in this case, the beneficial effect of BNC will be checked in the uniform plastic region, and there we calculate the index based on that one. If we use the entire section, we have the same results. We only can emphasize and compare the materials better if we zoom in on the region where the micro mechanism leading to a better performance is also emphasized. So there, if we now focus on that index, we can again see a better behavior for B and C. But in this case, we cannot attribute radial cracking to be the reason for this. There should be something else that is responsible for the better performance for B and C compared to A. What is different? Well, we have an additional density of carbides. So let's take a look to TDS again to check our trapping. And if we do just an analysis on samples as received ABC, we only have low temperature peaks. So we only have low and high angle grain boundaries being responsible there for the trapping. If we do a TDS after the test, so this means the test has been, there was a tensile test taking place in the presence of hydrogen. We take that tensile sample after fracture and we go to the TDS, then we see a different profile. So the mechanical loading apparently leads to this shoulder and also this high temperature peak. And this is linked to my story from the beginning that temperature can help to overcome a barrier to go inside a certain trap site, while mechanical loading can do the same. you can see that for alloy A, B, and C, we have for each of them a low temperature, 300-400 degrees shoulder, which can be linked to the presence of carbides. But more important, only for alloy B and C, we have a high temperature peak. And this high temperature peak can be linked to trapping inside. Remember, if it's high temperature, then it's really the vacancies inside the carbides that is responsible for the trapping, and this is absent for alloy A. So the better behavior we observe for B and C for the in situ testing, but in situ there is side cracking, so we don't have radial cracking. So the better performance can be linked to the beneficial trapping of these carbides present in B and C. We are continuing on this. It's not easy to analyze this sample because of the geometry, which is not homogeneous because it's a fractured sample, but it's clear that the blue one is not showing a high temperature peak while the other two are showing one. And then the final example, and then I will be hopefully in time, that's linked to the automotive sector and the role of retained austenite. Again, a good collaboration that we have with our friends from the Materials Center in Leoben. Let's take a look now to an easy microstructure, ferrite martensite. So there is no FCC present. So we have a BCC and a BCT microstructure. And then we do permeation to check the diffusivity. This is a well-known technique. And we add some mechanical load to that. We always like to have the effect of load on our testing, both the trapping and the diffusion. So we have a constant load proof ring, and we check the effect of elastic and plastic loads on the diffusion of hydrogen. If you do it for a simple material, so ferrite martensite, you can see that with 0% going to 60% of the yield strength. So there we are still in the elastic regime, we increase diffusivity. At 80 as well, and 100 we go back to the same level as 0. So in the elastic regime, we are stretching the lattice. Hydrogen has more space to move, so it facilitates its movement. So it goes faster. When we have microplasticity taking place from 100% of the yield strength, so we have already some dislocations, some vacancies, we can see that we have additional trap sites, and this lowers your diffusion coefficient. If we further go to the plastic regime, we further decrease the diffusion coefficient. So this is linked to the fact that mechanical elastic loading can increase diffusion. Quite understandable in this microstructure. Now we went to a second one, the QMP, so quenched and partitioned steel. That's a bit more complex because we have martensite, but we also have some FCC. We have retained austenite, both in a bulky and in a filmy way. So at the martensite, we also have some filmy retained austenite. We did the same permeation testing under load, and in this case, we see a continuous decrease of diffusion. So going from 0 to 50 to 75, we always decrease diffusion coefficient. And this is different than the observation in dual phase steel. In dual phase steel, in the elastic regime, we had an increase of diffusion. Now we see we always have a decrease. And that's quite surprising in the elastic regime because you're stretching a lattice. What is the reason? Let's take a look now. If we do without mechanical loading, we do our TDS, we can see that we, in the middle graph, we have only a low temperature peak. So only low temperature peak, no retained austenite is charged. Retained austenite is a quite strong trap of hydrogen, so it would appear at higher temperatures. If we do now a TDS after the permeation under load, so we have our sample in the permeation cell, it's under load, we do the permeation test, then we take that sample after the permeation under load and we go to TDS. What we then see is the appearance of the higher temperature peak only if we have load applied. So with 0% of the yield strength is red, there is no high temperature peak. If we go to 50, 75, 100, 125, we have an increased peak at around 600 degrees, which can be linked to retained austenite. The question is now, how do I know it's retained austenite? This is always with complementary microscopic testing. So we did some high temperature XRD, and we saw that the FCC peak was disappearing at around 500. And again, also some DSC was done, differential scanning calorimetry, and we can see that peak 3 and peak 4. This is the conversion. So there, your retained austenite is no longer stable, and it converts to bainite at that temperature. So it means that your retained austenite is disappearing, and this is the reason that we can observe the high temperature peak in TDS on the right top corner. So this is nicely showing that retained austenite can trap hydrogen, but we cannot calculate a diffusion and activation energy from this because hydrogen is not detrapping from the defect or from the phase. In this case, the retained austenite is changing because of the temperature change. You do basically a tempering step, you do a ramping, and at 500, you start converting your retained austenite. It decomposes at that temperature, and it goes to a BCC, BCT type of microstructure, and this leads to the desorption of the hydrogen. Okay, with this, I would like to thank you for your attention, and I'm open to any kind of question. Thanks a lot.
Thank you for your great presentation with a lot of interesting and very useful information. And now we are open to discussions. Are there any questions? No, maybe I will start. You show us a lot of beneficial ways to improve hydrogen entitlement. And what are you thinking about this performance of materials improved by these ways under long-term operation? It will be influenced on the performance or not?
If I understand your, yeah.
No, you can improve hydrogen entitlement by adding the carbide or improving grain boundaries, yes, but how it will behave under long-term operation?
Yeah, this is linked to the point of the temporary and continuous exposure, I assume. So it's temporary, so only a certain amount, for instance, a certain period of overprotection when you have CP applied on your system or some corrosion taking place, then you have temporary ingress of hydrogen, and then deep trapping by carbides or cementite can be interesting to mitigate your embrittlement. If you go to oil and gas and you have a continuous exposure of hydrogen, high pressure, or another environment where a lot of hydrogen is produced, then this is no longer beneficial because even these carbides, if they are incoherent, they can also be the initiation point of fracture because hydrogen can recombine at that region. Then the mitigation shifts a bit more towards the environment, for instance. If you talk about H2 gas, then some inhibition can be thought of, for instance, by the addition of oxygen or carbon monoxide. This can delay hydrogen uptake in the pipeline system. So this can also be helpful then to lower your amount of hydrogen in your material. So this is one way. So it shifts a bit the focus from the microstructure to the environment if you have a temporary or continuous exposure of hydrogen.
Yes, thank you. Are there any questions? No?
Maybe one
Okay,
question.
Professor Sabali.
Yeah. Thank you for a nice and very interesting report. And I would like to ask you about the structure of the additional phases or some inclusion phases which are responsible for the high temperature hydrogen. Yes, this is where phases with which structure? With this regular structure or amorphous structure?
For the high temperature trapping of hydrogen, this was linked to the presence of retained austenite, so the FCC structure.
Yes, but with this regular structure, with this maybe with this amorphous, or maybe with this structure with a lot of vacancies, or something about this.
Yep, I'm not sure if I understand your question. The audio is not ideally, but FCC is known to have a much higher solubility for hydrogen and a lower diffusivity. This is one thing, and this is linked to indeed the trap sites which are responsible for the trapping, so the interstitial positions, which are different in an FCC and a BCC structure. Both of them are crystalline, so the amorphous structure This is less linked to the metal application. So that's a bit more difficult to respond to. Yeah.
Okay, thank you. Are there any questions? Maybe online? No. Okay, thank you again for your great presentation and very useful information for our understanding of phenomenon of hydrogen embeddlement. Thank you for your presentation.
My pleasure. Thanks for the invitation. Thank you.
Okay, now we'll proceed with the next presentation. We have invited speaker, Professor Besson, from Center of Materials at Paris, France. The title of the presentation, Effect of Partial Oxygen Pressure on the Hydrogen Embeddlement of the pipeline steel. Please, Professor Besson, the floor is yours.
Well, thank you. I'm trying to share my presentation on my screen. See something?
Yes, we see, but in not in.
Now I'm in presentation mode.
Okay, now it's okay.
Is that okay?
Yeah.
Okay. Okay. So thank you for the kind invitation to this conference. Today I'm going to speak about the effect of partial hydrogen pressure on hydrogen embrittlement in pipeline steel. This work has been done within the framework of the French industry chair, which we called Messiah. And I would like to acknowledge the postdoc work of Pilar Fernandez-Pizon, who spent half of her time trying to work with the experiments and the modeling I'm going to show. So, oops. So what is the context? We all know that we want to transport hydrogen in existing or modern pipelines. And as we know also, there might be hydrogen embrittlement. So the idea that people had in France is, why don't we add some oxygen in the hydrogen mixture so that it could form some kind of protective layer. And that's what we started to study in this work. So what is the material? So that's a modern grade steel. It's close to X52 pipeline steel. It's a seamless pipe with a thickness of about half an inch. So it's not a very thick pipe. This is a modern steel, so there's a very low inclusion content. The sulfur content is very low, so that gives us a very high ductility material. On the micrograph, you can see that the microstructure is a mixture of ferrite and perlite. Okay, so to do this, to do the test, we use a machine that we developed at our research lab, which allows us to do tests under gas pressure. And in order to avoid having an ATEX environment, we have a pressure chamber here that is very small, which implies also that we need to use very small specimen. The load is measured by a load cell within the chamber, and we have windows to track, for instance, the crack tip opening or the crack mouth opening, or the necking in tensile sample. At the end, we also have a precise measurement of the gas to check that there is no pollution. So using this machine, we are using that kind of specimen. So it's a relatively small specimen. You see the diameter is 2.4 millimeter, and the length is only 22 millimeters. So very, very small. So we have been indeed conducting tests in air and under pure hydrogen. So under hydrogen, we are going to use 100 and 200 bars. And we are also going to have slow rate test, that's 10 to the minus 5 per second. On fast test, that's 50 times faster at 5 to the minus 4 per second. And we are going to do the same kind of test, but with some oxygen added to the hydrogen mixture with 50, 100, and 500 VPPM at the two pressures and at the two rates most of the time. Okay. So let's have a look at the results. For instance, this is a series of tests carried out with a pressure of 100 bars, except under air, indeed, with a fast strain rate. So here you have the diameter contraction. This gives you a very local measurement of straining. And it's very nice because you can get the load, the steady load drop that you get here. So the black curve corresponds to the test in the air. So as I said, the material is very ductile. The red curve is under pure hydrogen, and the intermediate curves here, I don't know if you see my pointer. The intermediate curves here correspond to the various amount of oxygen in the mixture. So we get a lot of necking under air, cup contracture. Under pure hydrogen, we get a lot of surface cracks and an almost fully quasi-brittle fracture surface. If we add some oxygen, so we still have surface cracks, but you can easily see that the necking is more important. There is more deformation before full failure. And at the center here, there is a little bit of ductility remaining. So now, what happens if we change the strain rate? Here you have an example under fast strain rate, 200 bars. So if you compare to the previous set of experiments at 100 bars, then there is a little bit of ductility reduction. We still have surface cracks. Now we do the test at the slow strain rate, 10 to the -5 per second. And you see that on the force necking curves, the curves have a different shape. You see that at the beginning, the curves under hydrogen or mixture of hydrogen or oxygen are very close to the curve under air. And then they drop all of a sudden here, here, and here. And if we look at the surface of the specimen, we don't see cracks, maybe a little bit here and here, but we don't see big cracks as we saw on the fast test. Necking is less important also, and this is probably because failure was initiated inside the specimen. We can define an inhibition effectiveness index, which is based on the reduction of area. So it's here. So you have the reduction of area for the mixture minus the reduction of area under pure hydrogen divided by the reduction of area with air minus the one under pure hydrogen. And what we see is that as we increase the partial pressure of oxygen, then this effectiveness index goes to 0 by definition, and sharply increases at the beginning, and you tend to get a plateau after a while. Apparently, we never recover full ductility, will never protect fully the material. So that's what I like to do. I have all this experimental database, and I want to develop a material model to simulate those tests. So we use a multi-field finite element model, which will integrate plasticity and damage. We are using a non-local Gerson-Tverger Niederland model for that. And indeed, we have to take into consideration the coupling with hydrogen diffusion. So we have two non-local variables. One is related to the plastic volume variation, that is growth of voids, and one which is the equivalent plastic strain, kappa bar, which is there to describe the nucleation of new damage inside the material when it's strained. For instance, carbides breaking or grain boundaries breaking and so on. So we use a fairly simple implicit gradient model for the non-local damage model. And then we get this equation for the damage growth. So that's the growth, the damage due to growth. On here, we have the damage due to nucleation. On one of our considered nucleation mechanism is nucleation of very small cracks, which is due to HEDE. And we assume that this rate of damage depends on the plastic strain, but also on the principal eigenstress sigma 1. And indeed, this AN parameter allows to introduce a coupling between diffusion and damage. For the diffusion model, we use the fairly simple Oriani equilibrium with only one trap family. And once again here, the flux of lattice hydrogen is you get the standard fixed term and also a coupling term with the mechanics, which is controlled by the gradient of the pressure. There's another coupling because we consider here, based on some other publication in the literature, that trapping will evolve as we strain the material because one of the trapping mechanisms is dislocation trapping, and the dislocation density increases as the material is deformed. So here is the, I will skip that, just look at the simulation we have. So we make a mesh of the specimen, very fine in the central area where the material is going to fail. The mesh size here is about 10 microns. On the outer boundary, which is blue here, we will include a model to reproduce the inhibition effect by oxygen. So what we know from other experiments is that if you put a specimen in the chamber without straining it, hydrogen will not enter the material, at least for usual test duration. The maximum we tested for, in our case, was 1 day. With straining, hydrogen will enter the material. And we know also that the presence of oxygen will reduce the kinetics at which hydrogen enters the material. So what we use here at the boundary is a Robin condition where the flux of hydrogen is related to the difference between the theoretical lattice concentration you would have at the boundary, and that's given by the Sievert's law, on the actual lower concentration. On RH here is an exchange coefficient. It is important in this modeling to consider that this exchange coefficient is not constant. It will increase if plasticity develops, for instance, like a curve like that, and it will decrease with time if oxygen is present, something like that. And the higher the oxygen content, the faster the reduction. So the differential equation for this exchange parameter is given by this equation, where here you need to have deformation to activate the boundary, and here that's the time-dependent term. At the same time, we want to model the cracks that are formed at the specimen surface. So we need to have an element removal technique like that. So that's the mesh. We consider this, we consider that this element is broken, so it is removed. But indeed, this creates a new surface that has to be created, and the exchange coefficient in these new surface elements has to be very large because that's fresh, a fresh surface that was not oxidized, or at least that was not modified by the presence of oxygen. And then we will grow the crack like that. So some simulation and comparison with experiments. So here you have the diameter reduction, the nominal stress. The simulation the simulation actually the dots. So that's under air and pure hydrogen and with the different mixtures here. So we get a fairly good agreement. What is interesting also is to see or to compute where damage occurs. So under air, there's a lot of necking, and failure will start from the center of the specimen. Under pure hydrogen, the surface cracks will appear, and one big crack will develop, and the specimen will fail. If we add some oxygen, because it's more difficult for the hydrogen to get into the material, then there's more necking, and there's a competition between ductile damage that grows at the center because of necking, and also a lot of small surface cracks that develop here because of the high concentration of oxygen close to the surface. And that was the high stress rate, the strain rates. If we now consider the small strain rate, whoops, you see that we also can manage to have a good agreement with experiment. But what happens here is that we predict that failure will initiate from inside of the material, which is what we guessed from the experiments. And that can be understood because if the test is slow, there's much more time for hydrogen to get into the material. So that's the hydrogen profile for the fast strain rate test. So you have the surface hydrogen, and when you create the crack, then the hydrogen will go at the crack tip using our varying boundary conditions. But here, there is a much less strong gradient in hydrogen concentration indeed. So how can we interpret that? For sure, for the slow test, the hydrogen concentration will always be the highest at the boundary of the specimen. But because of necking, you have higher stresses that develop inside the material compared to stresses at the surface, because at the surface, you have a plane stress state. So that's why the crack will initiate from the center due to the hydrogen present and not due to purely ductile mechanism, and the material will fail. Okay, so that's our interpretation of our database. In this presentation, I have shown that O2 can have an inhibiting effect on hydrogen embrittlement. We don't know exactly what happens for very long duration, as in pipeline operation. Plastic straining will favor hydrogen entry, so it's very possible that hydrogen does not get into the pipe if it's not deformed, if it remains purely elastic. But in case of an accident, hydrogen may get into the pipe very quickly. And we can reproduce the inhibition by O2 using a boundary condition where the hydrogen entry depends on both plastic straining and the O2 partial pressure, and these are opposite effect. There's a creation between the creation of fresh surfaces because of straining and the inactivation by the partial pressure of O2. Future work, we also have been doing tests on the small CT specimen, cracked specimen. We also have seen an effect of O2, but we need to do the analysis of this test. And that's the end of my presentation. I hope you could hear me. Thank you very much.
Thank you for your great presentation. And now we open to questions. Are there any questions? Audience? No? So I have a question. Do you suggest that controlling partial oxygen pressure in pipelines is a beneficial measure to control hydrogen embrittlement?
Yes. Yeah, that's what the result suggests. It could be helpful. But my feeling it's really helpful if you have some kind of accident. You imagine you have a strong deformation of the pipe, you create new surfaces because of plasticity, and then hydrogen could get very, very quickly into the metal, and then the presence of O2 will somehow heal the surface that is created and start protecting the material. There's a test we haven't been doing is pre-strain the material under, let's say, pure hydrogen, and then put oxygen, the mixture of oxygen, and see what happens. That could be interesting. Do we extend the ductility if after some straining we put some oxygen or partial oxygen pressure? That would be an interesting test to do, for instance.
And I'd like also to note that in pipelines we have some kind of corrosion due to humidity of, for example, for natural gas, and it can be also expected for hydrogen. And in this case, oxygen will accelerate corrosion. Do you suggest
Probably not.
Not?
Probably not, because everything is driven by the humidity and
Okay, and you presented the model, and do you suggest that this model can be applied also for other inhibitive additions, for example, for carbon monoxide or carbon dioxide or something else, not only for oxygen and for other additives?
Yeah, that would be, I mean, the framework will be working for CO2, for instance. There's no doubt about it. Now what I didn't mention, but you can guess, I mean, already if you just have mechanical loading plus hydrogen diffusion, these models are quite complex. You need to fit or find in the literature many coefficients, and that's difficult. Then you add some more coefficient to describe how the boundary evolves over time. So the main problem is the fitting, but in terms of framework, I think that this would perfectly work for CO2 inhibition.
Thank you so much for your nice presentation, and we hope that your future work will also include the influence of oxygen on fracture atoms. Yes.
Okay, I hope so too. I need time. I need time.
Important, yes.
As everyone. Okay, thank you.
Thank you so much for your nice presentation. And now we are going to the next presentation by Professor Shivanyuk from Kurdimov Institute of Metal Physics of the National Academy of Sciences of Ukraine. Please share your screen and welcome. Okay, can you open it in full screen mode?
Sorry, I cannot use my video camera, so just share the screen.
Okay, but we can see in full screen mode. Please press F5, yes?
F5, okay.
Okay, it's very nice.
Okay. Okay, thank you, Mrs. Chairman. I'm not yet professor, but maybe in future. Thank you. Ladies and gentlemen, my talk deals with physical nature of hydrogen-caused embrittlement in metals. I'm going to analyze the hydrogen effects in three main classes of engineering metallic materials based on iron, nickel, and titanium. So, among numerous hypotheses of hydrogen embrittlement, those of hydrogen-enhanced atomic decohesion, HED, and the hydrogen-enhanced localized plasticity, HELP, are the most widespread. Within the last decade, they were also united as HELP plus HED and HELP-mediated HED hypothesis. Their main features are the following. First, according to HED, the role of hydrogen amounts to the enhancement of normal stresses which exist at the tip and of the pre-existing crack and decrease interatomic bonds. Second, this crack propagates continuously due to atom-to-atom breaking the interatomic bonds. And third, any role of dislocations in hydrogen embrittlement is disclaimed. And according to HELP, hydrogen increases velocity of dislocations due to shielding the stress fields around the neighboring dislocations. This result was obtained in the theoretical calculations for the only edge dislocations. Using in situ TEM observations for different metals, the enhanced mobility of dislocations was confirmed. Both hypotheses were developed within the frame of continuum mechanics. The following remarks relating this hypothesis are very important. As shown first time by Yokobori, normal stresses disappear with decreasing thickness of samples, and they are completely absent in the amorphous metallic ribbons, where both plastic deformation and fracture proceed under shear stresses. Nevertheless, hydrogen embrittlement of these ribbons is not different from that of bulk materials. Formation of cracks under applied mechanical loading is always preceded by the nucleations of dislocations and their following slip. Presented here are the data of molecular dynamics calculations obtained by Katreshka and colleagues. It's shown that even in metals with prevailing covalent interatomic bonds, for example, in the molybdenum single crystal, subjected to the anexial tension, the applied stress causes the local shear and the reorientation of atomic planes, followed by nucleation and slip dislocations. Cracking and fracture come only after plastic deformation. And the result of these calculations were supported by sub-micromechanical tests performed inside the field ion microscope. And third remark, in all the existing models of hydrogen embrittlement, hydrogen atoms are presented simply as a point defects causing lattice distortions, whereas the nature of hydrogen as a chemical element is ignored. If so, any interstitial atoms are expected to increase velocity of dislocations if their atmospheres accompany dislocations during plastic deformation. Nitrogen and carbon atoms in iron and steel particularly suited for testing this idea because they are equal. They have the equal size in the crystal lattice, and therefore the shielding effects should be comparable. To test this idea, we used the internal friction technique in metals, the source of which is damping of mechanically induced vibrations of dislocations. Presented here is the Snock cluster relaxation peak of internal friction caused by slip of dislocations accompanied with carbon or nitrogen atoms in martensitic steels. The relaxation strength is proportional to the area crossed by dislocations during the vibrations. At constant frequency, it's a measure of dislocation velocity. One can see that in the comparison with carbon, nitrogen, dislocation acquire a higher mobility due to nitrogen. This conclusion is also true for the background of damping in austenitic steels where Snock cluster relaxation is absent. With increasing strain, velocity of dislocation is higher in the nitrogen austenitic steel than in the carbon one. Therefore, hydrogen-caused shielding of stress caused by neighboring dislocations as a base of the HELP theory is clearly overestimated. It seems more reasonable to take into account that as a chemical element, hydrogen should affect the atomic interactions in the crystal lattice. Mechanical properties of metals are controlled by the competition between metallic and covalent interatomic bonds, namely by the fractions of free electrons within the interatomic sites and those localized at the atoms. So free electrons prevail in metals from the 8th to 11th group of periodic table, namely iron, cobalt, nickel, copper, etc. And in this is a reason for their high plasticity. Localized electrons in the fifth and sixth groups, for example, vanadium, niobium, chromium, molybdenum, wolfram, are responsible for prevailing covalent interatomic bonds, and they cause brittleness. We use electron spin resonance that make possible to differ between the free and localized electrons in the metallic alloys and estimate their fractions. A scheme of measurements is present here. An appropriate microwave energy allows to transfer free electrons from the ground state to the excited one. The energy spent for this transfer is proportional to the fraction of these electrons. The spectrum of free electron spin resonance is presented in this figure for a paramagnetic austenitic steel before and after hydrogen charging, along with the reference sample having the determined concentration of electron spins. You can see that hydrogen significantly increases the concentration of free electrons. A reason for this hydrogen effect is a change in the distribution of electrons on their energy states. As example, the calculated density of states, of electron states, is presented in this slide for the hydrogen-free and the hydrogen-containing FCC ion. As shown in the insets, hydrogen increased the density of electron states at the Fermi level, which corresponds to the increase in the concentration of free electrons. The quantitative data are given in the tables for both FCC and BCC and FCC iron. Hydrogen in iron increase concentration of free electrons, enhancing thereby its plasticity. Along with hydrogen in iron, we studied this effect in nickel and titanium. In these metals, in contrast to iron, the hydrogen caused a change of density of electron states at a Fermi level is non-monotonous. First, it increases and thereafter decreases density of states. A reason for that is the miscibility gap in the nickel-ash system, creating the coexistence of two solid solutions with different hydrogen concentration and formation of hydrides in the titanium hydrogen system. The hydrogen caused increase in the concentration of free electrons softens the crystal lattice, decreasing thereby the shear modulus, which results in the following change of dislocation properties. First, a decrease of stress needed for emission of dislocations, for example, by Frank Reed source of dislocations, a decrease of dislocation-specific energy, line tension, which increase their velocity. A decrease of the distance between dislocations in their plane ensembles, pile-ups, which eases the opening of cracks. Therefore, the nature of help phenomenon can be derived from the hydrogen changed atomic interaction in metals. At least two hydrogen effects on the velocity of dislocations can be simply demonstrated using strain-dependent internal friction measurements. This is damping of vibrations in the hydrogen-free and hydrogen-doped austenitic steel caused by slip of dislocation due to periodically induced strain. It seems that hydrogen decreases the start stress for emissions of dislocations in austenitic steel as compared with to its for hydrogen-free state. Due to hydrogen, dislocation sweeps a larger area in the slip planes, which means their hydrogen increased velocity. It's remarkable that after hydrogen decaying, internal friction is recovered with some small increment caused by new dislocations emitted by the applied stresses. So hydrogen-enhanced localization of plastic deformation is the second important part of HLP phenomenon. It's not really interpreted in any available hypothesis. In the metallic alloys, it's obviously related with a short-range atomic order, namely chemical delamination of solid solutions. Hydrogen solubility is different in the submicro volumes of different chemical composition, and consequently, plastic deformation prevails in the areas with higher hydrogen content. Of course, this explanation is not applicable for hydrogen in pure metals. Based on the so-called void sheeting model proposed by Michael Ashby. With his colleagues, one can suppose that hydrogen-induced vacancies are the microvoids mainly concentrated within the hydrogen atmospheres at dislocations, which decreases the load carrying area along the slip planes. All the hydrogen damages in metals arise from the extremely high diffusivity of hydrogen atoms in the crystal lattice. This knock-cluster relaxation caused by diffusion hops of hydrogen atoms allows to obtain the values of the hydrogen diffusion enthalpy. As follows from this table, alloying elements in iron affect hydrogen diffusivity. In the nickel and the titanium alloys, the enthalpy of hydrogen diffusion is substantially smaller than in the gamma iron base alloys. The hydrogen convoy, the dislocation slip, is a precondition of hydrogen embrittlement. It's controlled by the enthalpy of binding between hydrogen atoms and dislocations. As example shown here, in the internal friction versus in inverse reciprocal temperature in a hydrogen-charged austenitic steel. At low temperatures, dislocations are blocked by immobile hydrogen atoms, and the damping does not depend on the temperature. With increasing temperature, hydrogen atoms acquire diffusivity, and the dislocations are moving escorted by hydrogen atmospheres. Dislocations cross a larger area from for the same time, so their velocity increases. According to Cottrell, the concentration of solid atoms at dislocation is controlled by temperature and enthalpy of binding, where K is Boltzmann constant. Treating the experimental data in the Arrhenius coordinates, we obtain two temperature areas of damping, above and below the so-called temperature of hydrogen condensation at dislocations. The slope of the high temperature branch in this picture is proportional to the hydrogen binding enthalpy. The data of hydrogen diffusivity and binding with dislocations, as mentioned above, are presented in this slide along with the temperature of hydrogen condensation at dislocations and for engineering metallic materials based on iron, nickel, and titanium. Hydrogen atoms start to accompany the slip of moving dislocations, and hydrogen embrittlement becomes possible below hydrogen condensation temperature. With increasing temperature, hydrogen diffusion increases, whereas hydrogen binding with dislocation becomes decreased. As a result, hydrogen atmospheres at dislocations become diluted, and the dislocations release them. Consequently, hydrogen embrittlement is expected to disappear. Therefore, based on this data, we can predict the temperature range of hydrogen embrittlement controlled by hydrogen diffusivity and hydrogen binding to dislocations. Some available data on the temperature dependence of hydrogen embrittlement in different materials are presented in this slide. You can see that the hydrogen-charged iron doped with a small amount of chromium, the temperature range of embrittlement is shifted toward higher temperatures with increasing strain rate, and embrittlement disappears at some critical strain rates. The high nickel austenitic steel 310 S is resistant to hydrogen embrittlement. With decreasing nickel content, some narrow range of brittleness exists in this 316 with smaller nickel content. Addition of nitrogen to these steels enlarge this temperature range because nitrogen atom pins the dislocations. In standard austenitic steels with the moderate nickel content, hydrogen embrittlement occurs in the rather wide temperature range. In contrast, hydrogen embrittlement does not occur in beta titanium alloys because hydrogen diffusivity is very high. Binding to dislocation is extremely small, and the hydrogen condensation point is below the temperature of liquid nitrogen. For this reason, hydrogen increases plasticity of beta titanium alloys, and it's effectively used in their technological processes. So summing up, one can state that hydrogen increased concentration of free electrons is a dominant reason for hydrogen embrittlement, and at the same time, the hydrogen increased plasticity of metallic materials. Second, hydrogen diffusivity and hydrogen binding with dislocations control the condensation of hydrogen atoms at dislocations, and consequently the temperature range of hydrogen embrittlement. So thank you for your attention.
Okay, thank you for your presentation. Are there any questions? Maybe one, two short questions? No. Are there any challenges for experimental proof of your electron concept? And also how it associated with hydrogen enhanced decohesion theory?
Okay, yes, we will check our electron concept for other structural engineering materials like aluminum, molybdenum, and not molybdenum, other alloys. So we will check how hydrogen affect on the electron structure and amount of free electrons in other alloys based on aluminum and other metals. So second one, which he did. Okay, yeah, indirectly our concept support HIDI because really metallic metallic bonding which enhanced by hydrogen weaker than the covalent one. So in some idea, yeah, some imagination, we can state that it supports HIDI mechanism.
Thank you for your interesting presentation. And now we go to the next presentation on sensitivity to hydrogenation of long-term operated and thermally restored steel of a steam pipeline vent of a thermal powered plant. The speaker is Ivan Zibailo from the Physical-Mechanical Institute of Sciences of Ukraine.
Good afternoon. So my report is devoted to sensitivity to hydrogenation of long-term operated and thermally restored steel of a steam pipeline vent of a thermal power plants. The outline of the presentation is the following: introduction, object of research, methods, results, and discussion, as well as conclusions. Decrease in serviceability of many steam pipeline of the thermal power plants is the influence of a number of operational factors, such as temperature and pressure of steam, corrosive hydrogenating technological environment, operating time, number of shutdowns of the unit during the technological process. All these factors is facilitated to the grip and fatigue of the metal, which contributes to the degradation of steel. The next slide illustrated structural changes in heat-resistant steel after long-term service. It is well known that long-term operation of low-alloy heat-resistant steel under elevated temperature and loads is accompanied by grip, which changes their microstructure. Hydrogen further accelerates the degradation process of this steel. Structural phase transformation in steel are associated with the precipitation and coalescence of carbides and increase in grain size. Chains of voids along the grain boundaries become energetically favorable sites for hydrogen, absorbed by steel during operation. All these voids are more easily combined into microcracks in the presence of hydrogen in the metal. This reduces the steel's mechanical properties and accelerates structural and lens fracture. Previously, repeated heat treatment was applied according to the generally accepted industry mode to restore the properties of heat-resistant steel after long-term operation use in the fastening elements of thermal power plants, steam turbine. It used made it possible to improve the microstructure and mechanical properties previously used steels. In this slide, devoted to the experience of using restorative heat treatment to extend to the main steam pipelines of thermal power plants, in particular to section of the vents. The purpose of the work is to substantiate the feasibility of using heat treatment to restore the structure and mechanical properties of steel after long-term operation in the main steam pipeline of thermal power plant, as well as to evaluate its sensitivity to hydrogenation before and after restorative heat treatment. The equipment used in this work and electrolytic hydrogenation regime are presented on this slide. This slide illustrates the optimal mode of recovery heat treatment and the relative number of grains of three size categories observed in the structure of steel from the stretched bending zone after the optimal mode of restorative heat treatment. For operated steel, a noticeable grain coarsening was observed, whereas after restorative heat treatment, the proportion of large grain significantly decreased, while the proportion of small grain increased. Moreover, this is a typical regularity for all levels of the pipe wall thickness. After applying restorative heat treatment, we expected the following: dissolution of carbides and homogenization of solid solution, reduction of grain and carbide size and pore count in the pre-operated steel, and improving the mechanical properties of steel by increasing hardness, strength, and impact toughness. So we can see that on the microstructure of steel in stretch band zone after restorative heat treatment. Maybe we can skip it. I will say shortly that after the number of carbides, we checked different sizes per unit area of microstructure images of steel in the stretch zone of bands after operation and subsequent restorative heat treatment. We saw that after restorative heat treatment, the number of large carbides in the inside grains increased, while inside at the grain boundary, this number significantly decreased. Also, after heat treatment, we saw that hardness increased to 170 HB compared to 120, 130 HB for the operated steel. This is increase in hardness is a good agreement with increase in the number of small grains. Mechanical properties of steel in stretch zone of pipe bands after long-term operation and restorative heat treatment was analyzed. As a result of thermal restoration, both structural characteristics and hardness improved significantly. An increase in strength, ductility, and impact toughness of heat-resistant steel in stretch zone of main steam pipeline band after restorative heat treatment, according to the proposed mode, was detected. Since restorative heat treatment improved the structure and heat properties of steel, it provides grounds to expect that its practical application will extend the service life of the steam pipeline components. The analysis of changes in tensile and impact characteristics of steel after restorative heat treatment compared to operated steel was analyzed. This analysis confirmed the effectiveness of proposed restorative heat treatment regime for restoring strength, ductility, and impact toughness of the steel, which is important for enhancing its serviceability. We consider this a strong argument in favor of applying restorative heat treatment to extend service life of main steam pipeline bands. This slide illustrates the effect of electrolytic hydrogenation on tensile properties of operated and restored steel. To assess the effect of hydrogenation on the stability of steel properties after restorative heat treatment, tensile tests in the air were carried out on smooth samples of both steel variants after their preliminary electrolytic hydrogenation. It was found that the hydrogenation of the operated steel worsened its strength and plastic properties. The characteristic of the restored steel, although somewhat worsened due to the presence of hydrogen in the metal, remained higher than the values regulated by industry document, was still in the original state. This slide illustrates the effect of restoration and additional electrolytic hydrogenation of steel on the change of its mechanical properties compared to the corresponding characteristic of operated steel. We noticed that positive effect of restoration was retained for all parameters. Even after electrolytic hydrogenation, the properties remained higher than those of the operated steel. Restorative heat treatment partially reduced the embrittling effect of hydrogenation. On this slide, fractographic feature of operated and restored steel from the stretch zone of steam pipeline band caused by hydrogenation was analyzed. Fractographically, cleavages area in the background of the tile relief were detected at the all structure of both variants of hydrogenated specimen. In the restored steel, there were found out only near large non-metallic inclusions, whereas in the operated steel, their number was significantly greater due to the large number of pores along the grain boundaries in which hydrogen could accumulate, facilitating the formation of cleavages. Thus, the identified improvement in the structure and properties of heat-resistant steel after using restorative heat treatment opens up prospects for its use to extend the service life of steam pipeline plants and thermal power plants. Can you please go to the next slide? Yeah. Then we can make some conclusion from this research, such as certification of the restored steel from hardness, strength, plasticity characteristic, and resistant to brittle fracture confirmed a significant improvement of all these mechanical indicators compared to the corresponding characteristic of the operated steel, justifying the feasibility of using restorative heat treatment to extend the life of long-operated critical elements of thermal power plants steam pipelines. It was experimentally shown that additional hydrogenation of samples after restorative heat treatment, according to justified mode, the positive effect of restoration, although somewhat reduced, still remained positive. While all properties of the operated steel under the influence of hydrogenation additionally decreased. This proved that the use of the proposed treatment is legitimate for extending the service life of steam pipeline elements, even under hydrogenation conditions. Cartographic studies confirmed that the proposed restorative treatment of the operated steel significantly reduced the manifestation of its hydrogen embrittlement. Brittle cleavages on the fracture of the treated steel were preserved exclusively in the vicinity of large non-metallic inclusion, which remained in the steel structure even after the treatment due to the loss of cohesion with the matrix. That's it. Thanks for your attention.
Thank you for your presentation. Are there any questions? Can you tell us about after your restorative treatment, do you expect any changes in hydrogen uptake by steel?
We thought that it will help, not help, that it can happen, but we are working on this and we will try to experimentally show how it will be.
Okay, thank you again for your presentation. And now we have 20 minutes break, and we will continue our work at 16:10.
Thank you.
Okay, I think it's time for a coffee break. Yes. Okay, dear Professor Olga, I think it's time for coffee break.
Yeah.
Okay, and when we will meet together again?
16:10, according to the program.
Okay, thank you very much. So.
Okay,
Ігор Юліанович, нас чути?
Давайте мікрофон переключимо.
Так, я вас чую, а зараз я...
Повністю свій екран.
Чи видно мою презентацію?
Ми
Так,
бачимо
видно.
вашу презентацію. F5. Нажміть.
Так. Вона в такому варіанті може бути?
Ні, спробуйте F5, або тепер ми бачимо. Спробуйте
О,
поспробуйте.
тепер це є вже F5, правильно?
Так, скролити,
О,
спробуйте.
окей. Все добре. Я тоді готовий. І чути мене нормально.
Дуже добре вас чути.
Окей, тоді так домовилися. Давайте я зараз, в принципі, її залишаю.
Все одно перше я буду вас оголошувати. Відключайте мікрофон, Юліанович.
А хто мені підкаже? Тому що я бачу тільки свою презентацію, а, як кажуть, учасників я не бачу і себе також. Це можна якось...
Алло, Львів, в нас іде трансляція на YouTube, вона не зупинена, тому прохання перевірити технічні аспекти, а всю іншу дискусію винести поза трансляцію, якщо
добре.
можна.
Добре. Hello to everyone. Do you hear me?
Yes, we hear you, Victoria.
And in the session hall, are you hearing me?
Yes, we can hear you.
Yes, thank you. So we can start. Or we need to wait for the Kyiv team. So I think that we can restart our session dedicated to hydrogen material science. And my name is Victoria Podhurska, and I will be chair in this part of our session. If it's okay with my sound, I continue. So now we have a keynote presenter, academic Igor Zavali, with his topics new manganese hydrogen-based composite for efficient hydrogen storage and generation. But first of all, I want to introduce him to audience in order to know our famous scientists. So, Professor Igor Zavali is an expert in hydrogen-based energy storage, working on, first of all, materials for hydrogen storage and battery applications. The second, nanomaterials and their properties, and for sure, high storage system. He acted as a project leader in a number of domestic and international research projects, and he is author of more than 200 scientific papers. So, Professor, the floor is yours. You have 40 minutes, and I kindly ask you to keep the time limit, because after oral session, we have poster session, so we need to look time, pay attention for the time. So, you are welcome.
Okay, thank you, Victoria. Good afternoon to all. And my talk will be devoted to the such class of materials as composite materials for efficient hydrogen storage and generation. And these results are obtained mainly Physico-Mechanical Institute in the Department of Hydrogen Technologies and Alternative Energy Materials. And first of all, I would like to say some introduction about hydrogen energy. It is well known that the hydrogen is an efficient energy carrier for future, and the main advantages of this carrier is the highest calorific value, 142 millijoules per kilogram, and the absence of polluting emissions during combustion. Yes, this is very important because the global warming is continued, and the fossil fuels is the lack of fossil fuels, and therefore all world are working on the implementations of hydrogen devices, of use of hydrogen as energy for future economy. I think we can emphasize two possible main directions of the use of hydrogen as a fuel. This is the use of hydrogen for transportation. And here you can see the picture with the Toyota Mirai, with such a famous, well-known model of a car, which is equipped by a fuel cell, by nickel MH batteries and by to balance with hydrogen and with this compressed gas hydrogen and balance with some maybe 60 liters with the pressure 70 megapascal of hydrogen. There are a lot of problems to the expansion of the use of such transportation because the hydrogen infrastructure. Therefore, now there is the second main direction for the wide use of hydrogen is the scheme which contains such elements. This is where some alternative sources such as wind or as solar. This is the electrolyzer which is used for the generation of hydrogen. This is the storage of hydrogen in the form of metal hydride accumulator or balance with pressed hydrogen, and this is the fuel cell. This is the scheme could be used in order to accumulate the electricity and in the form of hydrogen and to supply the hydrogen to fuel cell and obtain electricity in the place and in the time when we need. Okay, and now about the hydrogen storage and about the novel materials for hydrogen storage. As we know, the gas hydrogen and even pressed gas hydrogen is not very safe technology, and the capacity is not very impressive, and therefore a lot of other methods to store hydrogen are in progress. To develop new method to store the hydrogen are in progress. One of such methods are metal hydrides, with the compounds of hydrogen with metals or intermetallic compounds. The history of such materials maybe started in 1970s when the lanthanum nickel 5 intermetallic compound was discovered as the effective hydrogen storage material. The capacity, the weight capacity of this material is near maybe 1.5 to 0.0 weight%. And from that time, a lot of new compounds and a lot of new materials were discovered. And this trend is developed further. What are the main parameters of a metal hydride which could be used for hydrogen storage? The scheme on the picture, you can see from the left side the metal atoms and some hydrogen atoms introduced in this lattice. This is the alpha phase, and from right side you can see beta phase, or metal lattice with hydrogen atoms as regular structure. This is the metal hydride, the schematic presentation of metal hydride. The capacity of such compound could reach 2 or even 3 hydrogen atoms per 1 metal atoms. This is high capacity. And what are the main parameters of such system? The main parameter is the dependencies of pressure of hydrogenation, or the hydrogenation from hydrogen concentration and temperature. And these parameters for the different systems are very different. Why lanthanum nickel 5 is popular and is used for this time? Because the moderate temperature are necessary to absorb and to desorb hydrogen. The same situation is with the pressure. this material and other materials with higher capacity could be used for hydrogen storage. The other very wide application of this kind of materials is the metal hydride electrodes. We could say about the electrochemical hydrogen storage materials. This the electrochemically hydrogen storage materials are used as negative electrodes in nickel metal hydride batteries. On this slide, you can see some examples of hydrogen storage units which could be used for different applications, for some technical applications, as well as to supply hydrogen for fuel cells. From the right side, you see the small and simple hydrogen storage unit, which contain from steel cylinder and from maybe lanthanum nickel pipe on lanthanum nickel paint-based alloys, which contain some amount of hydrogen. And from left side, you can see some more complicated device with some heating system and which allow to supply hydrogen with necessary hydrogen pressure and temperature. From the right side, you can see also some applications of such systems. Recently we finalized the project, or we participated in the Horizon program project where such hydrogen storage systems were used for some transportation from some loader with the big hydrogen storage unit and some fuel cell which were used for such transport loader. And now about the main characteristic of hydrogen storage materials. I think that the main characteristic, besides the hydrogen plateau pressure, temperature of desorption, the main characteristic is the hydrogen storage capacity. Here you can see some scheme which demonstrate the hydrogen storage capacity for different hydrides, from aluminum hydride, magnesium hydride, and other intermetallic hydrides of intermetallic compounds. For some estimation from different institutions, where necessary, we need 6 weight percent of hydrogen in the materials to prepare to use the effective hydrogen storage material. Not a lot of hydrides correspond to this demand. Only aluminum hydride, but this is very expensive and it is very difficult to synthesize such hydride. Magnesium hydride, this is material which correspond to this demand, but it has some advantages and disadvantages. Sodium aluminum hydride correspond to this hydride, but the cycling stability of such materials, as well as cycling stability of other complex hydrides is too low, and therefore the main attention of many researchers were concentrated on magnesium hydride. And you can see that the main advantages is the high hydrogen storage capacity. For magnesium has 7.6 weight percent capacity, reversible absorption, desorption, low cost, non-toxicity, and so on. But there is very substantial disadvantage for this material. There is high temperature of absorption, desorption, low speed of absorption, desorption, and low cyclic stability. What is the reason of a main disadvantage of high temperature of absorption desorption? From the right side, you can see the structure of magnesium hydride, hexagonal structure of magnesium hydride, and you can see picture with the distribution of electron density in such structure. You can see that you can see some maybe a light blue color between the magnesium atom and between the hydrogen nucleus, and this is the experimental evidence of existence of covalent bonds between magnesium and hydrogen, and this corresponds to the high stability of this covalent hydride, and it corresponds also to other parameters such as diffusivity of hydrogen in magnesium, which are responsible for the disadvantages of this material. And if the functional parameters of this hydride as a material for hydrogen storage could be improved, yes. And two main directions, or maybe three main directions we can discuss in the frame of I would like to present in the frame of my report. The first direction is the improving of microstructure, reducing the size of the grains, creating defects, and creating of the defects. It could be achieved by mechanochemical treatment or mechanochemical synthesis of metal hydride. Second direction is the use of different catalysts as additions to the magnesium composites, and that direction is the structural modification and synthesis of new compounds. Okay, here you can see also some standard methods for the preparation of different alloys and composites. This is typical methods such as arc melting or such as mechanochemical synthesis. It means ball milling in hydrogen atmosphere, and some others. Besides such well-known methods as X-ray diffraction, scanning, electron microscopy, TEM, and others. Okay, and now again about the preparation of magnesium-based materials as effective material for hydrogen storage. Here you can see some description of a different method of synthesis of magnesium hydride. The traditional method of synthesis from gas phase. It needs high temperature, 350 degrees of Celsius, high pressure from 3 to 10 megapascal, and long time. And degree of conversion is not 100%. When we use the mechanochemical synthesis, we can reach 100% conversion at much lower parameters, at room temperature, at lower hydrogen pressure, and for comparatively short time, from 4 to 6 hours. And the picture, you can see some kinetic dependencies of some curves of hydrogenation upon the ball milling in hydrogen for magnesium, and magnesium with some catalytic additives. And you can see we can reach high storage, high capacity, but the time of hydrogenation is very different. It is much lower over magnesium with catalytic additive. And what is the product of such process of annealing? The product is the the magnesium hydride in nanocrystalline state. Means beside the small particles of a product, we can observe small nanocrystals in the structure of such ball milled in hydrogen material. Okay, and the first time maybe the magnesium hydride by ball milling was obtained by wife and husband Zalewski, Canadian scientist, in the middle of 90s, and demonstrated that such mechanochemical synthesis is the effective route to obtain magnesium hydride. And after this, maybe at the end of 90s, it was demonstrated that the use of some catalysts, the addition of some oxides, it seems it was niobium oxide and vanadium oxide to magnesium, accelerate the hydrogenation and decrease the temperature of desorption. Therefore, the studies of a system, magnesium with such catalytic additives is very popular from that time, and a lot of catalysts, huge amount of catalysts were used to demonstrate the influence of a catalytic additions on the hydrogenation properties of magnesium. We studied in our work some exotic kind of compounds, intermetallic compounds, so-called oxygen stabilized compounds with titanium to nickel type of structure. You can see here the structure with a cubic cell with 96 metal atoms in the cell, and such compounds exist in many systems. You can see here with the common scheme the systems where such titanium to nickel type structure exists without oxygen, and from right side you can see the systems where such compound exists by the oxygen should be added to the system in order to obtain this kind of compound. Therefore, the title, the name of that oxygen stabilized compounds is with this correct title, with this correct name, and this kind of compound, I don't know why, maybe because we studied the hydrogenation properties of these compounds, we used as catalytic additives to synthesize magnesium, effective magnesium storage materials. And here you can see some results. We used the titanium for iron 2 oxygen stabilized compounds. This is well-known intermetallic compound, and we obtained very good parameters of hydrogenation, kinetic parameter hydrogenation, and we also obtained the good desorption properties for such composites. We used 10 weight% of this intermetallic compounds, and in some cases we also added some amount of graphite. And we used for such system very substantial increase of kinetic parameters, and we obtained also very impressive decrease of desorption temperature. On the right side, you can see the picture, and you can see the poor magnesium poor magnesium. Magnesium hydrate is characterized by desorption temperature near 400 degrees of Celsius. Ball mill magnesium hydrate is characterized by desorption temperature near 300 degrees of Celsius, and the magnesium composite with catalytic catalytic additions from such compound is characterized by temperature lower than 200 degrees of Celsius. Okay, and with these two parameters, the hydrogenation, the desorption temperature, and the also very important parameter is the cyclic stability of such composite. And here you can see not very high number of cycles, but for only 20 cycles. But you can see that the such composite without carbon is characterized by quite quick loss of capacity. But when we added the carbon, when we added the graphite, we obtained the material with the stable capacity during the cycling of this hydrogen storage material. It means that we can use the catalytic addition, and we can use some graphite or carbon modification to obtain the effective hydrogen storage materials on the basis of magnesium. Here you can see also some PCT diagrams for this kind of material. The plateau pressure correspond to few bars. And also we started the hydrogenation of this composite in the second cycle. This is not the mechanochemical hydrogenation, this is hydrogenation from the gas phase. And we obtained the 6-weight capacity, the hydride with 6-weight capacity only at 200 degrees of Celsius. This is much lower temperature compared to that which was used to gas hydrogenation of poor magnesium. As you remember, poor magnesium from gas phase for hydrogenation need 350 degrees of Celsius. We studied also the desorption plots at this different heating with different speed of heating, and we calculated the Kissinger dependencies, and we obtained the very important parameter for such materials: energy activation of thermal desorption, only 67 kilojoule per mole. At the same time, the magnesium hydrate, this is for hydrate composite with catalytic addition. At the same time, magnesium hydrate without catalytic addition was characterized by an energy activation 46 kilojoule per mole. Very substantial decrease of activation energy. The similar composites we studied also with other representative of oxygen stabilized phases, and we synthesized the ternary hydride composite with zirconium-free, vanadium-free oxygen stabilized compound and graphite. And we observed also very good kinetic of mechanochemical hydrogenation of a material, and we obtained also the good temperature for desorption parameters for the thermal desorption of this hydride composite. And you can see here some pictures of the obtained material, and we also studied the X-ray diffraction patterns for these composite materials, and we observed the formation of two kinds of magnesium hydride, alpha magnesium hydride and gamma magnesium hydride, because the mechanochemical synthesis stabilized the gamma magnesium hydride. It is also very interesting observation. But besides these two phases, we also observed the hydride of zirconium 3 vanadium 3 oxygen stabilized phase with capacity 10 hydrogen atoms per formula unit. This is very high capacity for intermetallic compounds, and it means that this compound works not only as catalytic addition, but also as hydrogen storage addition. And this explains that the capacity as well as stability of thermal stability of this hydrogen composite, hydride composite is very good. Okay, and here you can see some additional studies of second hydrogenation of this kind of materials, and you can see very high capacity only at 200 degrees of Celsius, 6.5% capacity, and it is much lower temperature in comparison with that we need to hydrogenate magnesium from a gas phase. And also we calculated the Kissinger plots, and we obtained even lower energy activation, 58 kilojoule per mole. This is one of the best hydrogen energy activation which are described in the literature for the similar systems, for the similar composites. Okay, and it means the magnesium composite, magnesium-based composite could be used as effective hydrogen storage materials. Nevertheless, the temperature of desorption is not enough good for wide application, because for transportation we need maybe 100 or 150 degrees of Celsius, but we obtained the material with 200 degrees of Celsius of desorption. So it is not so promising for very wide applications. Nevertheless, the other applications of magnesium hydrides are also possible, and one of such application is the use of magnesium hydride for hydrogen generation. The use of this hydride to obtain the hydrogen, and this is the hydrolysis reaction. When the magnesium hydride interact with water, we obtained the magnesium hydroxide and gas hydrogen. And capacity of such system, the productivity of such system is 6.58%. And here you can see some installation to study the hydrolysis process, and we studied our systems also for the hydrolysis generation of hydrogen, and we use magnesium hydride with zirconium vanadium oxygen catalytic addition, and we obtained more than 700 milliliter per gram of our system only when we used the magnesium chloride solutions. In pure water, the productivity, the production of hydrogen was much lower. And we studied a lot of systems for hydrogen generations. We studied other compounds for the synthesis of composites on the basis of magnesium. We use also the titanium for iron 2 oxygen systems, and in many cases we obtain very good production rates of hydrogen near to 1,200 milliliter per gram for the similar systems where the catalytic addition was the intermetallic compound. But recently we started the system with nano-structured materials, very simple catalytic additives, iron and cobalt or nickel and cobalt, and we obtained very good, previous systems were characterized by the conversion degree from 75 to 85%. When we used nanostructured catalytic additions, simple nanostructured catalytic additions, iron, cobalt, or nickel, which was obtained by leaching, we received the generation more with the more than 90% of conversion. With more than 90% conversion, it means that the nanostructured character of a catalytic addition is very important for different parameters, for kinetic of hydrogenation, for desorption temperature, and also for the generation of hydrogen. And here you can see some devices, for example, magnesium hydrogen storage tank and fuel cell device. This is very small fuel cell, 30 watt fuel cells, and with some volume for some container for magnesium hydrate, for water, and some converter, and the system can produce the hydrogen for fuel cell, and such system could be used for some portable energy supply system. Okay, and besides this, I mentioned about the search for some other compounds on the basis of magnesium, which could be used as effective hydrogen storage materials. We studied different systems and we found in very simple system, magnesium, titanium, nickel, new compound, magnesium-free titanium, nickel 2. Also with titanium, it is characterized by titanium to nickel type structure, already mentioned by me, and we studied the hydrogenation properties of this compound. We obtained the not very impressive capacity, but we obtained very high capacity when we used elevated temperature. And the responsible for this very high, quite high capacity was the disproportionation reaction. The compound was disproportionated in hydrogen atmosphere with the decomposition to other hydrides and to other compounds. And also we tried to synthesize some more complicated materials, more complicated intermetallic alloy, which consisted the poor magnesium and the ternary phase magnesium-free titanium nickel 2. And it was more complicated system when single phase ternary compound or single phase magnesium. We selected the composition close to eutectic composition, magnesium 82, titanium 4, nickel 8, and we observed the high capacity is near or even more than 5% at 20 bar pressure and at 200 degrees of Celsius. This is lower capacity in compared to poor magnesium, but this eutectic alloy is characterized by much lower absorption temperature and much lower as hydrogen absorption temperature. It means that it emphasizes common tendency where poor metal or poor intermetallic compound is not so effective as more complicated system, as for example, eutectic alloy or more complicated composite with different addition as catalytic addition or as carbon addition. And one else possible application of magnesium-based hydride is the electrochemical hydrogen storage materials. I mean, the materials which could be hydrogenated by electrochemical methods. And we started from magnesium with carbonyl nickel, a magnesium to nickel compound with nano nickel, and we obtain the starting capacity of material more than 800 of milliampere per hour per gram and near 1,300 milliampere per hour per gram. This is much higher capacity in compared with industrial negative electrodes for metal hydride electrodes. The main disadvantage of this material is the cyclic stability. The capacity go down with cycling, and this is the problem, and we can look for some additions in order to stabilize the starting parameters of these materials, and in this case we can obtain the very promising and very effective electrode materials. Okay, and there are maybe some other applications of magnesium hydride, yes, and even we can say about some military applications. Recently we hear about some explosions on the basis of magnesium hydride, which was demonstrated by Chinese scientists or military scientists, but this is the theme of a separate discussion. And about the presented materials, I would like to formulate short conclusions. The magnesium-based composite materials with addition of catalytic some phases demonstrated the lowest parameter in comparison with similar systems which were described in the literature, namely energy thermal desorption, energy activation was 67 and 58 kilojoule per mole. This composites also demonstrated very good cyclic stability when the graphite as additional additive was used. Also, this composite materials could be used for hydrolysis generations of hydrogen, and when we used the nanomaterials as an additives to the system, we obtained very impressive conversion degree, more than 90%. And also this kind of materials could be used as negative electrodes for nickel image batteries in the case of the stabilizing of their cyclic stability. And that's all, dear colleagues, and I would like to present our team. This is Vasil Berezovets, Alexander Kononyuk, Yuri Verbovitsky, Andrei Kitsa. This is team of scientists from Physical-Mechanical Institute, and our partners from Norway, Professor Yatis, Dr. Roman Denis, also our partners from Ukraine, Professor Yuri Solonin and Oleg Yuzhun from Institute of Problems of Material Science, and our foreign partners, also Professor Pecharsky, Dr. Valery Polbunkur, and Peter Zavarin. Thank you for your attention.
Thank you, Professor, for your interesting presentation. You finished it almost in time.
Yeah,
but we still we still have a few minutes for maybe there are some questions from the audience. Maybe I will start.
Okay.
In the one of your first slide, you showed information about aluminum hydride, that it has high weight percent of hydrogen, and it was about 10%, 10 weight percent. This is the maximum value, or it's possible to reach more? 10%.
Yeah, I think it could be reached more than 10%. For example, some complex hydrides are characterized by more capacity than 10%. But the problem is not only the percent of hydrogen. Yes, for example, CH2 has 25%. Yes, the problem is not only the percent. The problem is the other parameters. Temperature of desorption, temperature of absorption, and so on. No, stability and many other parameters.
Okay, and when you talk about commercialization, it's obviously that in order to make your product more suitable for market, it should be comfortable. And how long, how many minutes or hours do you expect it to fuel your hydrogen storage system?
You mean?
How many minutes or how many hours do we need to fuel this storage device?
Yes, no. How many minutes we can fuel the storage device? It depends from the capacity of a hydrogen storage unit. Yes, but if you mean if we can use magnesium hydride long time, it depends from the conditions of how we can keep this metal hydride. Yes, when we keep the metal hydride in air, it can oxidize, and the functional parameters will be lost. But when we keep it in hydrogen storage, I think it is enough time to use this material as a hydrogen storage unit.
Okay, thank you for the answer. Maybe there are some questions in the chat. If no, I thank you again for your great work, and I wish you a nice, great future and obtain the great results. Thank you.
Victoria.
Thank you.
Okay.
Yes, and now it's my turn. I also want to present some information, and please tell me if you can see my slide, my presentation.
We can now?
Yes, we see.
And I try to slide to the next, and please tell me if it's work. Can you see the second?
Yes, it works. It works.
Okay.
We see the second.
Okay, thank you. So allow me to present a report about the study of properties of promising materials for interconnects a lightweight solid oxide fuel cell. With the development of civilization, the types of energy source are changing. Now we can see great interest to renewable energy, but at the same time, more and more attention is being paid to hydrogen energy. Why is hydrogen a fuel of the future? First of all, because it's the most abundant element, yes, making up around 90% of the known universe. The second one is that no CO2 emission. When hydrogen is combined with oxygen and ignites, it forms only water and releases heat. Hydrogen energy density. Storage potential. Converting renewable energy to hydrogen via electrolysis allows it to be stored for the future and at the same time stabilizing the energy grid. Hydrogen can also be used as fuel to power energy-intensive industrial process, such as metal processing or glass manufacture. And it's also very important fact that strong investment. From International Energy Agency, it shows that more than 1,500 low-carbon project now is realized. And the green hydrogen market is projected to reach 7.3 billion by 2027. And it's also a very important factor. Forecast, but nowadays we cannot see so many hydrogen devices on the streets, for example. But forecasts indicate substantial market growth. And for example, sorry, I can see this in my figure. For example, for hydrogen fuel cell market is expected to achieve $155 billion by 2032. And analysis predict that by 2040, hydrogen consumption will be predominantly in the industrial sector. But from 2050, hydrogen demand in transportation sector will increase. And cars and trucks seems the most promising technologies. This growth is supported by our scientific research and development efforts to enhance the efficiently and cost-effective of hydrogen technologies. One of the ways to use hydrogen directly as a fuel is through a fuel cell. This is a device that directly converts a chemical reaction into electricity. An elementary fuel cell consists of a dense electrolyte surrounded by porous electrodes, and interconnects are used to deliver fuel and oxygen and remove the reaction products. To increase the efficiency of fuel cell, they are assembled into the stack. And in this photo, you can see the ready stack of solid oxide fuel cell. In our research, we studied materials for intermediate temperature solid oxide fuel cell. Why did we choose this type of fuel cell? Because they are relatively inexpensive, and they combine a high electrical efficiently. You can see this, it's in the range of 50–60%, with a wide range of generation capacity. You can see 1 kilowatt, 100 kilowatt, and this makes it possible to broaden the scope of different applications. Currently, ferritic chromium steels are widely used as interconnect materials. You can see these materials. According to the literature, of course, considering the density of steel, about 80% of the total stack weight is due to the interconnect. You can see these diagrams. In terms of total cost of the stack, interconnects account around 45%. So in our opinion, the search of optimum materials, for optimum interconnect materials for intermediate temperature solid oxide fuel cell is an important material science problem. To find suitable materials, it's necessary to evaluate all requirements for such stack components. You can see in this slide these requirements. It's a high electrical conductivity, high oxidation and corrosion resistance. Its thermal expansion coefficient should be close to another cell components. Mechanical strength and toughness, and chemical compatibility. For a long time, this type of fuel cell was considered also for stationary application. And naturally, that in this case, the weight of the stack was not an important factor. But however, times are changing, and so are technologies, and now we can see that about possibility and prospects of their use in a mobile device. So is why the weight of this fuel cell stack now is becoming an important factor. The idea of our study was to replace the traditionally used steel with titanium materials. And this allows us to reduce the stack weight almost 2 times. Why titanium materials? Because titanium is known lightweight structural materials. It has good corrosion resistance, has good electrical conductivity, thermal conductivity. You can see this is in this line. His coefficient of thermal its thermal coefficient expansor is very close to the another materials of components. And during 2025 years, we implemented a NATO project, lightweight solid oxide fuel cell for energy security, where one of the task was to development new titanium materials for solid oxide fuel cell interconnects. So our materials and methods. The main characteristics we investigated were long-term oxidation resistance and electrical conductivity, surface electrical conductivity. Oxidation was tested at 600 Celsius degrees and for 1000 hours. Since a fuel cell has separate anode and cathode sides, we also divided our study into 2 environments: cathode atmosphere, it's mean air, and anode atmosphere, it's wet hydrogen. According to literature data, we use 30% of water vapor. For experimental test, a special installation, you can see the scheme, was developed to provide exposure under a controlled atmosphere. As a parameter of oxidation resistance, we use mass gain per unit in milligram per centimeter square. Surface electrical conductivity was measured using 4-point probe methods, both in the initial and post-oxides states. For our research, two groups of titanium materials were selected. First group is titanium composite based on MaxPhase, and the second group is titanium alloys. Based on our experience and literature data, we applied the following alloying approach. By adding such elements like aluminum, zirconium, tin, and silicon, the oxidation resistance will be improved. By adding such elements like niobium, tin, and manganese, will increase the electrical conductivity in the post-oxide state. It should be noted that in our investigation, Crawford steel is currently used as interconnect for interconnect fabrication, was also investigated in all these conditions. The studied composite based on MaxPhase demonstrate high strength, you can see in this table, and stability under elevated temperature and hydrogen environment. As mentioned earlier, the main characteristic that we studied were long-term oxidation resistance, this is figure A, and electrical conductivity, figure B, in this slide. It's known that Crawford steel has very high oxidation resistance at 600 Celsius degree in the air. And we can see that our titanium composite based on MaxPhase 211 structure type and composites alloyed by tin, so they have oxidation resistance very close to the Crawford steel. But the significant advantages of tin alloyed MaxPhase was observed in terms of electrical conductivity. After 1,000 hours exposure, you can see that titanium composites maintain conductivity at the lower boundary of conductors, whereas Crawford steel degraded to the level of semiconductors. On the graph, these red lines, you can see this in the figure B, these lines mark ranges distinguishes conductor, semiconductor, and insulator. And we can observe how it changes during the time. Investigation in anode environment, I mean in bad hydrogen at 600 Celsius degree, are more complex. So only the most promising materials were tested in this environment. The results indicated that both materials and Crawford steel and the best titanium composite has worse oxidation resistance in these conditions. And after 1,000 hours, both materials became insulators. Microstructure analysis of titanium composites surface after a long-term exposure in the cathode environment showed that in addition to oxygen, all the original composite elements were preserved. XRD analysis confirmed the presence of a main MaxPhase 211 structure type and there are 4 different oxides, titanium, aluminum, and tin. But in our study, we are interested mostly in the upper layer. For this purpose, we use Raman methodics more precisely for surface investigation, and Raman spectroscopy detected the formation of titanium oxide, but in the anodized modification on the surface. This is red line. After exposure in anode environment, XRD no longer detected max phase. We can see only 2 oxides, titanium and aluminum. So it indicates that oxidation was more intensive. And important fact that titanium oxide was detected only in rutile modification. So from these results, it can be concluded that high surface electrical conductivity of the titanium composite in the cathode environment is provided by anatase type titanium oxide. And in contrast, more intensive oxidation occurs in anode environment, and rutile type titanium oxide formed on the surface. What about titanium alloys? It's evident that titanium alloys has obtained by casting and after this thermodeformant exhibit higher mechanical characterization compared to titanium composite. But obtain mechanical properties significantly exceed the recommended values. So we don't need so high mechanical properties. And what about oxidation resistance? Almost all titanium alloys demonstrate very high oxidation resistance. Its value mass gain per unit square less than 1 milligram per centimeter square. However, alloys with high content of alloying elements such as silicon, this is number 1, niobium 2 and 3, and with high amount of aluminum 9 and 10, all these alloys demonstrate that electrical conductivity rapidly decreases and corresponding to value of insulator already after 250 hours exposure. And we can see that only titanium alloys number from 4 to 8 exhibit very high surface electrical conductivity after a long time exposure, and this is really great results in our project. So we can tell that we can recommend this titanium alloys as interconnect materials in the cathode environment. Unfortunately, our results obtained in anode environment was not so successful. Materials number 7, which don't consist tin, showed the poorest oxidation resistance and electrical conductivity. And alloys 4, 5, and 8 that have a very similar doping element demonstrate very similar behavior. But it should be noted that after 1,000 hours exposure, they showed surface electrical conductivity on the level 2.10 minus 4 Siemens per meters. And even it's not very good values, but it's better than for Crawford steel that we have obtained before. Raman, okay, microstructure and XRD analysis confirm the same that we obtained for titanium composite. And I just want to emphasize that the same results we obtain in the cathode environment on the surface. We have titanium oxide with the anatase structure, and from the anode environment we obtain titanium oxide with rutile modification. So let me conclude it. What I see, this upper part, I just put this in for future discussion maybe, but the main conclusion is the next. We strongly can recommend such titanium composites and titanium alloys as interconnect materials for for solid oxide fuel cells from cathode side. From the anode side, they require a little bit improvement, and we already know in what direction we have to move. And the main results, in my opinion, is that it has been found that electrical conductivity of the oxide surface of titanium materials was provided by TiO2 oxide with anatase structure, and we think that such elements like niobium, manganese, and tin will help with this. My report is completed. Thank you for your attention, and if you have some questions, I'm glad to answer for it. I can see in the chat, but chat is no any questions.
Questions from Francevich Institute of Problems of Material Science. Please, Alexandra Vasilyev.
Thank you very much, Victoria, for, as usually, great report and interesting information. I don't. I wouldn't actually go into very fine details you discussed about the alloys you used and so on and so forth. There is no doubt it's a great high-level research done there. But if I may, I have several questions about maybe motivation or something like objective setting things. And please consider this as my curiosity, not some attempt to put some maybe shadow. So my first question, you mentioned intermediate temperatures. Could you please clarify what that means and why these materials are important for intermediate temperatures and not so much for other regions?
Thank you for the questions. First of all, about motivations and this temperature. During this is not very new technologies. Yes, this is known maybe for in such way, maybe century fuel cell is not new technology, but there are Depending on electrolyte materials and operating temperatures, there are several types of fuel cells. And we deal with high temperature fuel cells. It means solid oxide fuel cells and molten carbonate fuel cells. Why we choose this type of cells? Because of efficiently. We started in this project with solid oxide fuel cells because we have some team from your institute that created anode and electrolyte materials, and because of this we started to deal with such type of fuel cells. But at the beginning, because of possibility of solid electrolyte, it works under such type of fuel cells works under a very high temperature, and even upper 800 Celsius degrees. But as I said, time changing and so are technologies. Yes, and now scientists found another electrolyte materials that can work at less temperature. Because you know that the higher temperature we have, the most challenger for material. It's not very good for each materials. And it was tendency to decrease working temperature, and it was estimated that 600 degrees it is minimum that we can reach. We can.
Victoria, I'm sorry for interrupting. So again, intermediate temperatures, are they intermediate for the ceramic fuel cells? 600 degrees C when where you studied your materials, are they intermediate?
Yes, 600 degrees, this is intermediate because they usually works at temperature higher than
Other lower
8.
temperatures. Other lower temperatures than
It's
600 degrees.
impossible for such type interconnects
So
because of possibility of
these are low temperature ceramic fuel cells, no?
there are another type of fuel cells with another electrolyte. For example, alkaline polymer fuel cells. It's another type of fuel cells.
Yeah, but for ceramics, it's the lowest temperature possible. So it's not actually
Because
intermediate. Intermediate would be something like 700, 750. Am I right? Or
no.
Okay, thank you. I think the discussion goes south. Sorry. If I may, one quick question more. 90% of hydrogen universe is composed of 90% of hydrogen. Is it right? Is it correct?
Yes, I found this information in the internet, and I didn't check.
How much of that hydrogen is actually easily accessible to us on Earth?
If we talk about water, we have really possibility to reach hydrogen, for example, by electrolyzers. Yes, maybe with reforming, not only green hydrogen but blue hydrogen.
So most of hydrogen is already in some compounds. We need
yes, we
solve
don't have pure hydrogen, unfortunately. So we need to obtain it from some reaction. So you know about this gradation with different color. Yes, green hydrogen from the water by renewable energy, black from free-forming hydrogen. Yes, we need to obtain this pure hydrogen and then use as a fuel.
Okay, so I think I don't agree with you that it's unfortunate that hydrogen is not easily accessible as a pure substance. Probably we would have a lot of explosions. Sorry for maybe a little bit silly questions, but it was my curiosity I wanted to satisfy. We have more questions here, I think.
Okay, thank you very much for very interesting talk. And I have one question about titanium dioxide modification. As I understand, do you use anatase and rutile modification of titanium dioxides? But it is well known that anatase transform to rutile at 600 degrees. How do you prevent this transformation in your devices, in your cells? Thank you.
Hello, Madeleine. I'm very happy to see you again. And thank you for this nice question about modification of titanium oxide. But we started work with pure titanium. We don't formate specially this oxide. It forms during the long-term exposition. So it's as a result.
Okay, thank you. I understand the formation of titanium dioxide modification as the results of the exploitation of the working your cells.
Yes, yes.
Thank you
yes.
very much. Thank you.
Thank you, Victoria. There is no any. We have one more question, but I hope it's the last question for you for today.
My question is that is the developed titanium composites and titanium alloys, are they suitable for area-based solid oxide fuel cells?
Hello, Alexei. I also glad to see you. It's very very pleasure to me. And yes, for manufacture in wild amount for current collector of interconnects, it's not so easy. And now we are working under another way to manufacture such compounds, and we try to use more commercial titanium alloys, and they apply coating based of this titanium composite and titanium alloys, because we know that to commercialize we need to decrease price of the products, and this is our next stage. Thanks you again for your question.
Thank you.
Okay, thank you, Victoria. I think from Francevich Institute for Problems of Material Science, it was the last questions for today, but not the last questions for future. Thank you very much.
Thank you for your interest and useful for me questions. It's needed to know to understand how it sounds from the side. And now we are starting with our poster section as I chair of this session of hydrogen material science. But please explain me how we can to download this to this poster.
Victoria, if I may, Alexander Vasilyev,
Yes,
I will
yes.
say a few. We will open a presentation composed of the posters, all except two that belong to presenters from your institute. They wanted them to be presented.
Yes, I know.
Directly.
Yes. Mhm.
So you just announce the presentation. We show the slide, and the person, the speaker, turns on their mic and camera and start speaking. As soon as they have finished, you announce the second one, and so we go.
Okay,
Am I
yes,
clear
it's
with
clear.
that?
Yes, it's clear. And for each presentation, we have 5 minutes, yes?
Yep. Yeah.
So,
up to 5 minutes.
Up to 5 minutes. So a 7 poster presentation are planned in this poster section, and the first will be Ruslana Horda from Francevich Institute for Problem of Material Science. Is she connected? Yes, I see Ruslana. Hello.
Hello.
Can you open your poster slide?
one moment.
No, wait a minute. We will open the 5 slides except the 2.
Yes, okay, we are waiting for opening this first poster slide, and then Ruslana can start. From my side, I see this poster.
Yes.
So,
Thank
floor
you.
is yours.
Good day, everyone. My name is Ruslana Hurda, and I represent the Francevich Institute for Problems of Material Science in Kyiv, Ukraine. Today, I'd like to share work of modification 8YZ by multi-doping to increase its ionic conductivity. Ukraine has significant deposits of zirconium mineral, which nature source of zirconium dioxide. This gives our country the opportunity to develop its own raw material base for producing stabilization zirconia powders. These materials are important for medicine, structure ceramics, oxygen sensors, and especially for electrolytes in solid oxide fuel cell or SOFs. At our institute, a chemical laboratory was established to develop a complete method starting from zircon processing and ending with zirconium dioxide stabilized in different ways. The most common electrolyte today is 8YZ stabilized with 8 more percent of yttrium oxide. It has good conductivity and thermal stability, but there is still a challenge. We need to reduce the operation temperature of fuel cell while keeping high efficiency and low cost. That is why our research focus on cost stability on multi-doping as a possibility way to improve conductivity. We compared the properties of traditional 8YZ with a sample cost stabilized by several dopants. 2 more percent europeroxide, 3 more percent scandium oxide, 3 more percent ytterbium oxide, and 3 more yttrium oxide. We will call 2 europeo, 3 scandium, 3 ytterbium, 3 yttrium as that. Another this multi-doping sample did not show a higher conductivity than 8YZ. It demonstrated competitive value, which means this direction in still promising. Future work will focus on optimization, the dopant ratio, and explore a new combination to future improve ionic transport in zirconia-based electrolytes. That's all. Thank you for your attention.
Thank you, Ruslana, for your presentation. So we move on, and let me introduce the next speaker. This is Dmytro Brodnikovsky from Francevich Institute for Problem of Materials Science. Is he present? Dmytro, are you
Dear
with...
Victoria.
Hello, Dmytro.
Dear Victoria, please name our institute simply. Francevich Institute. Stop.
Francevich Institute. Thank you.
Without these long tails.
Thank
Please,
you for the advice. Yes, thank you.
You're welcome.
So, is Dmytro here? Maybe he will join us later. So we move for the next presenter. This is Olena Semenova from Frantsevich Institute. Is she present? So we are listed again, and the next speaker, Ihor Polishko from Frantsevich Institute. Is he presented? Again. So, but Natalia, I saw that Natalia Kunik et al. Are present.
Yes.
Also from Frantsevich
I'm
Institute.
present. Okay.
You have 5 minutes, please. The floor is yours.
Thank you. It is known that nanocrystalline fuel nanosheets, two-dimensional, 2D molybdenum sulfoselenide substantial solid solution are promising as nanoelectrolysis for green hydrogen production via water electrolysis, as well as for the development of new electrocatalysis based on nanocomposites with synergetic effects. This work presents the results of structural studies of homogeneous molybdenum sulfoselenide. You can see a table with the results of X-ray studies on my poster. Also the electrochemical investigation as electrocatalysis for the hydrogen evolution reaction. Electrochemical properties of 2D molybdenum sulfoselenide were studied in 0.5 molar sulfitic acid electrolyte using the potential dynamical polarization curve method. Platinum was used as a counter electrode and silver chloride as the reference one. The working electrode is shaped as you can see on my poster, and were prepared by cold pressing at 15 megapascal. The results of this work you can see on my poster, and there's interesting problems relevant to this term, hydrogen and water intercalation process in the 2D nanostructures, synthesis of nanocomposites during prolonged contact with air, and change of semiconductor conductivity type of these nanocomposites, and the use of onic electrical contacts and the formation of corresponding heterointerfaces. Also cold sintering behavior related to preparing of working electrodes for research, and surface hydrophobicity. Thank you. And for attention, there's only beginning of the work, and we are only on the beginning steps of this work. So we will go on in future.
Thank you, Natalia. Good luck in your future research. And we have the last 2 poster section from Physico-Mechanical Institute. And maybe someone join us from the
I'm sorry,
list.
can I put question?
For the poster presenter, if you wish, because we have time.
Okay, go on.
Are you going to ask questions or not?
No. Please continue. The
Okay.
next poster.
I just talk that I cannot see any another presenter. No, any Alexander Kononyuk. He is also absent, and Christina Vlad I also don't see them on the online chat.
Victoria, perhaps they are offline in Lviv? No?
No, they are not yet or will be.
So our section, poster section is greatly reduced, it seems.
Very quickly, yes. So in this case, I just want to thank all of you to join this session, this part of the conference. Frankly speaking, at the beginning, I wasn't sure that this idea is great to separate to the different sections, but now I feel I feel that you was right. Yes, it's great to combine different city and different scientists. Thank you as an organizer, and I wish you good luck because we have all week of this hard work. Yes, so I expect that we will successful in this. So now we
Thank
can
you.
close this our section of hydrogen material science. And by the way, Pane Sergiju, I very like this combination of words, material science. I very like this combination. So because of this, maybe I thought.
Francevich Institute, you save time.
But
save time.
but you see, we have time. Yes, it's very.
If I may join for a minute, the problems are the key. You have to say the
Problem.
problems because
Yes.
otherwise the institute is
Yes.
just.
But
so.
My specialty, I'm material scientist, so I'm glad of this, without any problems. So we can.
For joining the conference and for your help with moderating this section. It was great.
You are welcome.
Okay, let it be.
Sorry, can you repeat?
Yes, I think it's all for today. I think we can close our session and our first conference day. So thank you again to all the participants joining us today, joining us at plenary session, joining us at hydrogen
I like
material
this
science.
separation of oral.
Thank you and see you all tomorrow. At 9 o'clock, we start our next session. It's advanced ceramic and glasses. So see you tomorrow.
See you. Bye.
See you.
Have a nice evening. Bye.
Ну, назву то ми ж зробили, щоб розширити, але ж ну що робити так? Я поки в себе залишаю, завтра тобі віддам. Чи зразу тобі дати? Ну, буду. Тільки я там на 11, потім схожу на семінар до себе туди. Ну, наші якось так.